Tony, actually, we can't hear you.
Yeah, maybe you gotta come off mute.
Either to unmute yourself on the phone or on the PC.
Yeah, one or the other.
Okay, can you hear me now?
Yeah.
Now we can hear you, yes.
Okay. But so I would like to show you a few things that so yesterday I was playing around with the software analyzing the data. So there is three things I didn't really understand, and there is one question which made me a bit puzzled.
Okay.
So why does the blank look like this?
Right. So this is how it is. It's normal. So electrospray. This is an extremely sensitive instrument, and electrospray is a dirty, let's say, a dirty analysis technique anyway. So especially those of you who have maybe worked with a less sensitive instrument, or those of you who have done work on a triple quadrupole like MRM, you'll see this, and this is normal. And that's why I was quite surprised why we could actually see your target in the TIC. Okay, that's
I will show you why. But yeah, because I was a bit surprised. You told me that my compound is to the power 8, which is very high.
Yeah.
But we're looking at a blank, which is before you run anything else, and the blanks are pretty dirty. So I found that to be a bit.
Yeah. So that's why I recommend you the process that we talked about, where you have a true blank sample, which is the difference between your blank sample and your real sample is only the compounds you're interested in. And then you use the unknown tools in the analytics to try to remove all of those extra peaks. So one way you can check that everything is okay, and I'm not sure if you remember, but in the lecture we talked about the ITC lens, ion transmission control. So what we can do is to come here and to just look at the TOF trace. So this is now the TOF only. And if you just double click here at the beginning, you can see this is a little high, actually. I would expect below 20,000. So it's not too bad, especially at the beginning. The LC may have some, I don't want to say junk, but some oils and stuff left in it from the manufacturing process, which maybe need to rinse away. Normal background here at the beginning of the run, right, where nothing is really eluting, it's just the solvent. I would really like to see about 20,000. That would be the best.
Yeah, my problem is not with the solvent side. My problem is with the other peaks.
Yeah, so they're
since years now. It's been more than a decade I've been using top, and this is my own personal opinion. I don't really like to see this, especially if I would go on show PPC, and usually what mass tolerance would you put here?
Oh, well, this is high resolution, so 0.05.
All right.
Yeah, so 0.4 would be more for like unit resolution.
0.05. And then you still have peaks at 10 to the 6.
Yeah. Yes.
So this makes me detecting my peak not possible. So since you started having a look at our sample last week, I was a bit puzzled with what you found, but I've been looking at our samples, and to me they don't make too much sense, because there is a lot of whatever peaks we're seeing, which not all are plasticizers, but some are very weird peaks, and I don't get what's the difference between the gray peak and the blue peak.
Okay. All right, so step by step here. All your questions are great. Nothing is wrong. This is normal results. We'll just go step by step through. So to me, like I said, this is a little bit high, but this is not unusual in time of flight at this sensitivity level.
Okay.
you're going to see this. This is what you'll have to deal with. Now we can, that's also why when we had like the big picture talk that I talked about doing two things. And one is always to take half of your sample or a portion of your sample and spike in it something you know. For example, I said the triazines, just because I know you have it. If you want to use something else, something that's more similar to what you're looking for, that's also great. But then you have a control in your sample that you can process and identify, and that you know that your data processing is working. And the second thing would then be to have the appropriate blank. If you can get your blank as close to your sample as possible, ideally it would be that the only difference would be the compounds you're interested in. And I know that's not, I'm saying those words very easily. I know that's difficult sometimes, and you brought up the cost, and it's also expensive, I know that. But that makes the processing so much easier, because that unknown processing in the analytics side will then give you area ratio. And area ratio will show you what's different. So those are the two things that will make your life a lot easier. I understand they may be hard to set up, and they may be hard to do in the lab when you are preparing your samples and thinking about your experiment on that side, but it definitely makes the analytics a lot easier.
Right, so preparing a blank is a walk in the park, right? So whatever solvent you're using to prepare your sample, you just prepare one without your sample. But,
okay, yeah, that would be the easiest. But it would be
having a control, so let's say you have 20 samples, and then you have to make them 40 samples, because in each sample you need to add a control to make sure that the analytics are running fine. You just multiplied our expenses by 10, because you have to double the amount of solvent, double the amount of sample size, double the amount of tips, double the amount. So I'm going to walk you through every step at a time. I'm sorry I'm being boring, but what you need to understand is this is going to be a hell of a lot expensive than anywhere else in the world. We have a financial crisis, and we have too many samples to run. So if I'm to split my samples and if I'm to duplicate my samples, at the moment I have 286 samples to run on the LCMS. So that's going to be multiplied by 2. And then you're going to have to add standard to 286 and no standard to 286. And that's over around 600 files. You also have,
maybe just in a batch, you don't have to do it for every sample. If you have if something is similar.
What samples that didn't really work? So what would you blame? You would go back and you would.
Well, in a batch, if I had one control, and that worked, then the assumption would be that all the samples in that batch worked. You have the calibration check, and you can also go in here. So you produce the base peak chromatogram here at the bottom. So maybe just for the other folks here, does everybody know what it means, base peak? So it's a really simple term. Base peak is just the biggest ion in the mass spectrum. Not the biggest, sorry, the most intense. The most intense ion in the mass spectrum. So in this mass spectrum that we're looking at right here, the 185.1149, that's the base peak. So what the base peak chromatogram is doing is it is looking at the most intense ion at every time point, and it is showing you then a chromatogram of the intensity of that. But maybe they are not the same mass all the way through, because if we look, for example, over here, right here, the base peak chromatogram, here the base peak is 338.34. So the base peak chromatogram is a simplification of the data to show you what is the most intense ion doing at every time. So what I would do from your base peak chromatogram is go and look at one of these peaks, right? And okay, here's the base peak, the 282, and then I would just make a selected ion chromatogram just of that. And now you see, okay, I have a decent peak for that. So that is a confirmation to me that everything is working okay, because the chromatography system is producing a peak. So I guess I would like to change my statement, if I may, because I guess I didn't realize that you had quite so many samples, and I do agree with you, that is a huge cost. I was thinking about it that you might have one sample or two samples, in which case I was saying to split the sample and to spike. So what I would do with a sample set that has hundreds of samples is just take one or two of them and split them and spike in the controls.
Oh.
And
But-
that way you can be sure that the batch is working. That's what I want to check.
All right.
So if you don't mind, I'll just adjust my answer there. Because yes, I agree with you, taking 260 samples and making it for 520 or whatever it is, yes, crazy. I agree.
Okay. So
just something in your batch that you're confident that everything is okay.
okay.
And a sample, at least one sample where you have in it something you know, so that you can test your processing to find that.
Yes. So that's clear now. But so the second part of the question, on the BPC, you can see some peaks are gray, some peaks are blue.
Yes. So it
What
has
does that mean?
so it's just an alternating color scheme to show you where the mass changes, I believe.
Okay.
So you will see that also, for example, if you go to any pane and you say show data and peaks table, this is the raw data, and I think I might have shown you this because I think my mind is a little fragmented the last 2 weeks because I did so many different customers, but I think I showed you this. I think someone was asking me about transferring the data to Excel in this group. I think it was this group. And so I showed you this, and I showed you the peaks. And then maybe I missed this point, but if you click on the fill peaks, you will also get this alternating color scheme.
Colors. Yes.
And just what that's doing is showing you, okay, this is one peak, making it a little bit easier for the visualization. So the base peak is, I think, doing the same thing. That change from blue to gray is where it changed the mass that is made up the base peak.
Okay. Can I show you something from a different data set?
Sure. Just maybe, if you don't mind, while we have this open, just let's ask the other folks if they had any questions from this, because you and I maybe are moving at a different speed than everyone else, which is understandable. But I just want to say, while this data is here, before we go to Tony's next section, does anyone else have any comments or questions on this or something they didn't understand?
And is anyone other than me not happy with the blanks?
So, you can see the system. I don't know how you prepared the water that we're analyzing now, but overall, I want to say that the data coming from your lab that we are looking at here is very clean. I'm very impressed with that. Some places I go to are just filthy dirty, and you see here in the TIC, you just see a huge, like it looks like a plateau. You don't even see peaks. So I want to say this is, in my experience, this is pretty good. So what you can do to prove it to yourself is, to take a very fresh blank, just be very careful and take a vial, and you can even use drinking water or something if you want to use a water different than what you have in the lab, and try it and see. But to me, that blank is pretty good.
Okay. Right. So I have just quickly, so I know what DOFMS is. What's IDA and what's SWAT?
Right.
One is for oxidation, that's IDA, and SWAT is for.
So we have those slides, and I think we'll just I'm sure you're asking, I'm sure the other folks have the same, so we'll just go through that again. So there are two ways of doing MSMS.
Mm-hmm.
And IDA would say, let's say the traditional way. In IDA, we select one parent and we fragment it. So the parent has a single mass.
Okay.
One Dalton mass. Let me just find the right slide here. Then I'll continue. We're way down. So, right. Okay. So in IDA, we are doing MSMS of single parents.
Okay.
And people say, and I make the same mistake when I'm talking, I say IDA is an MSMS. Actually, it's not correct. IDA stands for Information Dependent Acquisition. And this is the algorithm that is used to find what to do MSMS on. So IDA is actually the combination of a survey scan, which is a TOF-MS scan, and that's looking into the data, and it's seeing what's present at every cycle. And we set it up in the methods you have there. We set it up to choose 10 parents from that TOF-MS scan, and then do 10 separate dependent scans, which are 10 MSMS experiments on the 10 different parents.
Is it MSMS only or MS to the N?
So in this instance, we cannot do MS to the N. We have no trap.
It's MSMS. Okay.
Yeah.
All right.
In this instance, we do MS or we do MSMS.
Okay.
So that is the IDA cycle. Is one survey scan, checking what's present, identify some targets, and doing MSMS on those targets and cycling around that. And we set that up to go to make a cycle, I think, in about 700 or 800 milliseconds. So it's doing those 11 scans every 800 milliseconds. So what do we get? We get a TOF-MS scan, which is shown to you here. And then the ions that have the star shape are the ones that are chosen. And we get separate MSMS for those. So this is very clean MSMS. We have MSMS of the parents. But in some cases, for example, you see here, there is a missing target. So this was not chosen. Why it wasn't chosen, let's not talk about that right now. But for some reason, it was missed. And if this is your target, then you don't have MSMS of your target. It's still present as an MS scan, but it's not there as an MSMS. So basically, SWOF can solve that problem if you know what you're looking for. So just some data. So what SWOF is doing is it is opening up the Q1 filter. Instead of filtering like we do in IDA, instead of filtering just one parent, now we are filtering a range. So we have a 25 Dalton wide range here, and the parents that are inside that range, they can pass. So you see red, green, light green, and blue are in that range. Tan and gray do not pass because they're not in that range. And actually, we call that a SWOF. An English word, SWOF, means a range. And they are fragmented together, and then we have the high resolution to separate out the daughters. And we move through the mass range with different swaths. So the idea would be in this picture, one swath would be one of these combine harvester machines moving, and then the next swath, and the next swath, and the next swath, and so on. So this would be 25 Daltons here, and from here to here would be your whole mass range. So the idea is we get MSMS of everything, but it's all jumbled together. All the daughters are jumbled together. So these two methods, IDA and SWOF, are kind of working together almost. IDA has clean MSMS, let's say traditional MSMS. SWOF is dirty. SWOF has everything, and IDA has to pick and choose. Now, for your work, you are primarily looking for new things or unknown things. I would say we'll do almost always the IDA. The swath is really only useful if you know what dollars to look for.
Okay.
So that would be if you were doing library searching, or if you were doing quantitation. Both of those experiments require you to know what you're looking for. So you have a library. Maybe there's a lot of things in the library, but still you're looking for the things in the library. And quantitation, you have a standard and you're doing quantitation, so you know what you're looking for. So that's kind of the difference between the IDA and the swath. In your work where you're identifying new things and basically doing structural elucidation, you always want to do IDA.
Okay. So
what we did in the data was we just collected all three, so you would have a data set that you could play with that has each sample in the three different ways.
Okay. So I will just quickly show you with the ones with the triazine, the IDA of
So the
this
B.
one and this one. Let's come to IC. So
So that actually looks a lot better.
yeah, but this was meant to be at best 2 peaks because it's by NMR, it's 95% pure.
Yes, well, we have heard that before.
Yeah, I know. But so the question is, from that list, so I'm not really familiar with the software yet. So if I want to go back, what I usually do is I close the.
Yeah, this is much better actually. So I'm not sure what changed between looking at the other sample we looked at and this one, but this one is much cleaner. So
Well,
maybe
more
already
samples.
things are rinsing away. Pardon?
More samples were run.
Yeah, so it's getting cleaner. Yeah, that's what I expect at the beginning. Okay, so well, I mean, you've got two ways to do it, right? So I tried to, when we talked on the last day, I think, I tried to show you the two different ways. You're welcome to come here to explore mode and to play around, but it is a little bit like finding a needle in a haystack.
Okay. So there is another way I know, which is somehow it's similar to cheating, but it actually works. It's by actually using the PDA or the VIII detector. But what I found strange in this run is that the PDA detector gave a really bad spectrum, as you can see, while in another run it was quite okay, and I could identify what I was after. So the IC gave a very strange readout, I don't know why, on all wavelengths.
Well, I'm not sure why that is. As far as I know, is the flow go? Obviously, the flow is going through the VIII because we see the injection spike. So in my experience, we may not see anything because we spiked the triazines at like 20 ppb, right? I'm not sure the UV will have that sensitivity.
Yeah, but so the triazines are at very low concentrations, but my compounds are not that low because in another sample I can actually see them. So maybe I can show you. This is what. And then I would go on the extracted wavelengths. If you look only at these three wavelengths, here you go. And this is the UV. And you see these?
So in this
Peaks.
case, you have peaks. Yeah, I mean,
Yes.
um,
But I still don't understand what's this, because this should not be there. So this wavy set of peaks, this should
yeah.
not be.
Well, there may be that
Air bubble.
that may be, yeah, it could be an air bubble, or it could be a polymer set.
Well, polymers would probably affect the MS, but not the LC in my experience.
Yeah, we don't see it in the MS. I don't have my experience. Yeah, unfortunately, my experience with DAD is almost zero since 20 years. So I'm not sure what that specifically is caused by. There shouldn't be an air bubble. There was an air bubble stock. Why would we see it only when there's high acetonitrile? Or I don't know. I guess you're using methanol. Or
Air bubble was, maybe the air bubble was coming from the organic solvent.
Could be.
Okay.
But it also.
It could be that the inlet of the filter that takes the solvent from the bottom to the pump was a little bit above the surface. That would make sense in the organic solvent.
But this is the samples we reran. This is not the first set, right?
Yeah, this is the one we have. But we have. Yeah. But
so
yes.
I'm also wondering why the period gets longer.
Yeah, I think in the sample afterwards it goes away, or the sample is before. But before we solve this issue, can I quickly show you something about one of the peaks before we move on?
Sure, yep.
Okay, so let's say I want to. So how can you extract the PPC of this peak, for example, or this peak?
So this is the DAD data. So you would have to go into the base peak chromatogram here.
Okay.
So the first thing,
What's
I guess,
the offset between both?
I don't know. We'd have to calculate that from some known compound, I think. So now when you zoom, they are linked. So, it also can be, okay, you have a UV spectrum, but you don't have a mass spectrum. It's not known, it can be like that. So I don't know whether the linkage is that far. I don't expect it to be, I mean, this is you are using red tubing, I assume, on everything. So I would expect the delay to be something like maybe 0.1 of a minute maximum.
Yeah, this is 0.3 almost.
I would be very surprised if it was 0.3 like that. So it might be here. And then one of these ions, which is giving that signal. But unfortunately, that's for us to work out. There's no direct link like this mass gave that signal, right? Because we don't know what's the
but we have
ionization.
So we should be able to.
We have the what, sorry?
We have the triazines, no?
Yeah, but I think the triazines, we won't see it in the UV because it's not strong enough. So if you
what I'm saying is we have to do the triazines similar to this.
Oh,
so
yeah.
we have a bit stronger random check the offset between the UV and the X.
Yes, sure, you can do that. Okay. Yes.
Right. And one last question. Okay, supposedly I have this, and I want to figure out my MS. I want to get the MS spectrum of this guy.
Right. So you're in manual mode. So in manual mode, nothing is linked.
Yes.
So what I would do in that case is I would show the IDA Explorer.
Okay.
And the IDA Explorer, then what I'll do is I'll just you have to take some notes. Get a paper here. Come on. Okay, so what are we looking at? 1095.1788. And the retention time for that is 9.232. All right, so now I'm just going to hide everything here. Okay, so now in the IDA Explorer, we have a dot for every MSMS that we did, or that the instrument did. So we have to find now that mass. So here's 1095, and the retention time is 9.2. So it's going to be right in here somewhere. 1095 is here. 1095 1788. So probably
1787. This part.
1787 at the end there. Yep. So oops, I clicked nothing. Okay. So this looks like. So then I can click on this one to see the XIC. Okay, that is correct. And this is the MSMS here.
Okay.
So what you can do, and you can also click on this one to see the survey scan. And I believe this is kind of where we left off on last week when we were working.
Yes.
Hey, that's an interesting isotope pattern too. Look at that.
I know. That's a doubly charged molecule. No,
it's a doubly charged. Yeah, it's doubly charged, and it has some interesting maybe chlorine in it.
Yes. So supposedly I want to get the molecular formula of this, but from the MSMS spectrum. Is that possible?
And this is a loss. Sorry, and this is a common loss. So this is a loss of the same thing and then the same thing. So maybe we are looking at a plasticide. So the only way to get the molecular formula is then to do the formula finder.
Yes.
Formula finder from here. Then we link. And we select. Like that. So maybe here we need to choose, it's not MH plus though. I think, how did we get that to appear? We came to here, I think, right? And we said, yes, M plus 2. I will highlight a few more of these so you have it.
You need the M plus 2.
Sorry, this one, yeah. All right, there we go. We can define, and then so it is not recognizing that as a double charge, even though that's pretty close.
So my question is, so looking at the molecular formula involves a little bit more work. This is not my worry. My question is, can I look at the molecular formula of the fragmented MSMS?
Yes. Yep, yes. But
so I can load A27.6 and then look at the molecular formula of that.
So there's two ways to do it. One is as a fragment of this, so you can use the second button to link, like this.
Okay.
Yeah. And then say find, and then it will calculate MSMS details of this formula that it finds here, MSMS, and it'll plot here every peak in the MSMS, and if it is a good match, it'll give you a green dot, and it'll tell you the fragment piece, like this one is doing here, like for the parent. And then the second thing, I think you can also link, that's interesting, huh?
So this is probably one of the plasticizers and the pipettes.
I guess, yeah, it certainly is weird enough.
Yeah.
So I don't know if you can take the MS and link it here and go like this. Can you do that? Yes, it loads the data, and you can choose. Now it's double.
Yeah, because it's
So you can use an MSMS as an MS if you link it, fool it, and you link it using the MS, and then you have the formula finder for that. But keep in mind that fragments may not follow the same, let's say, organic chemistry rules as a parent, because the fragments are breakages. Yeah.
okay. And so one very last question, and I'll be quiet. I promise.
No, this is the right way to work, in my opinion. Oh, okay, yeah. My problem is I keep fooling with that formula finder until I get it right. All right. Continue, yeah, continue.
So is there a way, if I want to compare two samples of mine, is there a way I can do so?
So how do you compare them?
So I want to look at the chromatograms of, let's say, this guy and this guy.
Okay, so there's a couple ways you can do it. One would be in the analytics. You can do this area ratio of control and let it find the samples. In explore mode, you can open multiple samples here.
Mm-hmm.
For example, A and B. Let's just play with that for now and say, okay. And now the ticks are overlaid.
Okay, all right.
And then now, as you go through your analysis, you can maybe you'll pull out different extracted chromatograms. You can always use the truck to move them around. And if you want to do a subtraction or an addition here, you can use these two buttons. And again, it's like clicking and dragging, the same as how we did it to link the MS and MSMS. So you take the one that you want to subtract and you drag it to the target that it will be subtracted from.
Okay.
If you forget, you can hold your mouse here and it'll tell you how to do it.
Okay.
And the positive, it doesn't really matter which one you do because it sums them together anyway.
Okay.
So
and is it possible to actually go on and look at base peaks of both and the usual stuff?
Well, you have to do it, I think, one by one because only one can be active at a time.
Okay.
Yeah, let's try it. I have not done so base peak chromatogram of that and say okay. Yeah, you just get it for the one, I think. No, you can no. Sorry, it gives you the choice. The last choice is, do you want to do it for all the overlaid or the active only? So you can say all overlaid, and then you'll get a new one, which should be a double overlay, as we have two samples. Maybe it'll take a second.
Yeah, it should.
Because it has to do double work. There we go. Yeah. So now you have it both again overlaid. So
see, but it's disturbing for me because now A and B are the same sample, but one with triazine, one without, and triazines don't appear that late, do they?
Yeah, the triazines are up here, I think, if I remember correctly. I think, do we have it still in the extract? Yeah, here they are. So let me just... Okay. Yeah, so the triazines were in here. But at 20 ppb, it's not. They're not going to be the base peak chromatogram.
Yeah.
The base peak chromatogram is great, But to be honest, we are not using it so much because this instrument is so sensitive. It is kind of rare that your compound will actually be the most intense. I don't see a lot of people using it for that reason anymore. So, like on a less, I was using base peak chromatogram 20 years ago when the instruments were a lot less sensitive and they didn't have such the dynamic range and so on they have now. But now they're so sensitive they just pick up everything, and then the base peak chromatogram becomes a little bit less useful. So I do want to caution you. I think it's great what you're doing, but just be careful because if your compound is not the most intense, you'll skip it altogether.
Okay. Yeah.
If that makes sense.
All right.
One thing I want to see here, what is the... Okay, it's not too bad. 795,812. So what is that? That's that's 005. Okay, the retention times are pretty close. I would like a little bit better than that.
They should be overlaid.
Yes.
Because they're the same sample, so.
So you have 0.01 drift. That's not too bad, actually. 0.02.
Okay.
Because that is times 60. That's 1 second difference.
Okay.
It's not too bad. Just it looks hard. It looks worse here. So. Yes, and then you can have the spectrums overlaid too.
Yeah.
So just remember just to refresh your memory, when we did this, we did open multiple samples, not open sample. Yeah, open multiple samples.
I just have to get my head around the blanks because what I'm used to is a different kind of blank samples. The blank samples, we used to get them, so you would see the injection peak, you would see the change in solvents, but not that much noise on the MS. And it was a QTOF as well, but and sensitivity not far off this one. I mean, the max is 42 plus is I think a bit more sensitive than this guy, and the base peaks, the TICs of the MS were a bit less noisy. So this is why I was puzzled yesterday. I didn't understand what was going on.
Well, it could also be the ion source. The turbo V source is perhaps maybe a bit more bright, so it ionizes a lot of compounds. Could be. It'll clean up a little bit, but I wouldn't expect too much better than this. This is, like I said, I'm pretty impressed with how clean things are here.
All right. I'm done with my questions. Sorry to bother everybody, but...
No, actually, I think that was a great review of what we did last week. So I hope that was beneficial also to everyone. And maybe also you, by default, now become the super user. So everyone will come to you with their questions.
I wouldn't mind helping, obviously. So,
yeah. That's good.
So, Tony, are you satisfied with the blank and your results?
So, am I satisfied with the blank? Alek says they are pretty good. I'm still a bit scared or worried. Alek has more experience with SCIEX than I do, so probably go with what Alek is saying. If we have more problems, we can ask him more questions.
Absolutely.
Am I satisfied with my results? I think we need to get, how do you say, more hands-on work with the device. I mean, it's just only a few samples now, so...
Yeah, I think more familiarization.
Yeah, maybe we might set up another call with Alek in a few weeks after we did a few samples.
100%.
Yes, for sure we can do that in January after we...
after we ran a few samples, we did a little bit more work. We skipped this issue, so I don't know if everybody is seeing what me and Alek were talking about before, but Alek, can you zoom in on this part of the chromatogram?
Yes.
I don't know how to zoom in yet to the device, so.
Zoom in is always click and drag on the numbers of the axis.
All right.
Yeah, not in the picture and not
Yes.
below the numbers. It doesn't work. You have to do it right on the numbers. And then to zoom out, double click on the numbers. And the same for the Y. You can zoom the Y also. Same way. And then double click.
So what?
And that's true in any of our data.
Okay. So one of the things I don't like at the moment in what I see is this difference. So Alek is saying 0.01 second, which is not bad. But
0.02 minutes, which is 1 second.
0.02 minutes, yeah, which is 1 second. But for me, these should be overlapping. Because otherwise, if you're quantifying, then you have a problem. You cannot have something with a wider window. I think this is just, we need to get used to preparing the solvents properly. One person probably preparing the solvents, some organizational issues we need to discuss. Dr. Awaini.
Are these the same samples where you saw in the DAD these waves?
Yes.
And you were talking about the bubbles?
Yes.
So maybe this is why you have a small shift in the
But I mean, I think we are maybe discussing something that the instrument will consider trivial, because that difference is a second difference in LC retention time is pretty good, guys. Like we set up our peak finding in the software, either for quantitation or for unknowns. You know, we give it like 10 seconds. So 1 second is pretty good. Now, can it get better? Perhaps, and it may be that there are some error which is causing this. I'm wondering if it is not, if it's not related to the A pump. So it's showing up when the B is the strongest solvent. But if it was somehow related to the pumping of the piston, it could be the A, because at high time, high organic, the A pump is moving slower. Whereas at other parts of the chromatogram, the A pump is pumping faster and it's dampened out.
Okay, can you minimize this without closing from here?
You can hide.
So can you go back to the Explorer to load a different sample? I'll just show you something quickly about that.
So we didn't open the Explorer, I think, for this data. We closed it. But if you want, you can. You mean the IDA Explorer?
No. The Q, not Q. Explorer, the processing. So if you go here.
Sorry, you lost me. Yeah, this is where we were.
Yes. If you would minimize this, can you open new samples? No.
Oh yeah, absolutely. Yeah, sorry. Okay. Yes. You can have. It's just like Word. You know, you can work on many documents at the same time. Yeah. Sorry, I didn't catch your question. Yeah, absolutely. Yeah, just keep opening, and then they will show up under Windows. You can go to the Window menu, and they'll just be in the back.
Okay. So
I mean, at some point you'll reach a memory problem, but let's say that's after 10 samples open at the same time or something. So that's polymer, my guess. See, around 5 to 7 minutes, because we see it in the TIC. That would be polymer. We can check it. I'll show you how to check it.
we wanted to see the.
Yeah, you see that, how it shows up so nicely at the base peak?
Yes.
Around 5 minutes, 5 to 7 minutes.
See, it's very shallow. The waviness.
Well, I'm going to have to make a note and speak to someone else who knows more about DAD than me. Because it's like, right, there is that big peak at 12 minutes, and then after that, it's this resonance. Hang on one second.
Yes.
Excuse me, I had to sneeze. So there was, yeah, right after that big peak, thank you. Then right after this big peak, it was, this resonance comes. Okay, I will try to find out. My boss worked at Waters for a long time, so maybe he knows.
Right, Alek, can we now switch our focus to quantitation? And Zahra is with us in the lab now, on the next to the machine, and she can show us her calibration curve, and then we can take it from there.
Yes, sure. Just before we do that, let me show you one more thing about this. So this polymer here that's coming, you can do it directly from the TIC, or you can do it from the base peak, either way. But what you'll see is if you click on each one of these masses, or sorry, each one of these peaks, you will see that the mass is then different by the polymer unit. You see that? It's like a ladder. So we can get our calculator 5693137 minus 5252877. So that's a 44 unit. So you have a polymer of units 44, which is like PEG or something. I can't remember which one it is. So this is 44, 44, 44, 44. So that's an easy way to see that you have polymer. So I hope all the parafilm is removed and so on, and no more parafilm near the instrument. That can be a cause of that.
Yes. Okay, thank you, Alek.
Yep, you're welcome. My pleasure. And certainly keep in touch while that was me. Some feedback.
Alright, so Zahra, we are here on the PC, and then we can speak your data. First one by the calibration curve is on the cube. On the cube.
Yeah.
And just point to close this and open yours.
Maybe the last set of samples here?
Yeah.
All right,
Yes.
so...
Yes, here are the standards 1, 2.5, 5, 10 to the FMX.
Okay.
So,
And
yes, we want to now have to do a quantitation process to do the calibration curve.
all right.
Machine.
Okay. Sure, we can do that. So this is the triazines, or this is something...
Triazine with FMX.
What is SMX?
Pharmaceutical.
Pharmaceutical, okay. Can you type it for us so we can take a look? Sulfametoxazole. Okay, great. That'll work lovely. All right. So this is what we need to know. So first of all, we take a look at the structure. Just for metabolite ID, we have this compound, so we know this compound very well. And then what I do is I write down the formula, right?
Yes.
So we have C10.
C10 H11 and
3O3S. Okay. So when you do quantitation on this instrument,
yes.
you have to start with the formula.
Okay.
All right, so we get that information, and I like to just have a look at the compound and make a guess, and then that way what will happen, like I did with the nitrogen, and then that way you'll gain more and more experience of looking at the compounds and seeing what works and what doesn't work.
Yes.
So that's always a good start. And then we can go to the software.
Yeah.
And we're going to use the analytics page. So this is the analytics, and just to remind everyone, it's this part, right?
Yes.
All right. So to do quantitation, we have to start exactly what you did. You have to start with at least one standard. In your case, you have started with the standard curve, which is great. So we're going to come to results, and we're going to say new. And right now, we don't have a processing method. So we're going to start the processing of the samples you ran. And also at the same time, we are going to make our processing method. So the idea is to move to the right side all of the compounds, all of the injections. So we can take a blank, and we can take your whole standard curve here, right? And what is these are? This is a real sample. SMX
Yes.
at 120. That's
Yes.
an unknown sample. Okay, great. So we'll move that over as well. So we have a blank, we have the standard curve, and then this is your, let's say, unknown sample. Is that correct?
Yes.
Yeah. Okay. So then we'll say new.
Yeah.
And now we're going to make a method very similar to what we did last week. And then once we have the method, I'll show you how to produce the quantitative results in the chart. So the first thing we have to do from this page is to select a reference sample. So normally what I do is I choose something in the middle of the curve. So let's see, we can choose something maybe 40 or 60 ppb. And we will use that to process, or let's say to build the method. Now up here, you have the choice. You could go like this, and you could say, okay, I just want to do quantitation. However, on this instrument, because it's high resolution, I would always keep the targeted identification, because that way we can track the mass accuracy. And what you may find in quantitation is that for some reason, I don't know what could be, but for some reason, if your mass accuracy drifts and you're not watching it, it will look like your quantitation is failing. So that's a little confusing. I don't know if you remember, we talked about how to generate an XIC, right? And we talked about the XIC width. So imagine now you have a problem and you have a mass shift. Well, the mass will shift out of the XIC window. So what will that look like to you in the data? It will look like a drop in area. It will look like you're losing sensitivity. But actually, you're not losing sensitivity. You have a mass accuracy problem. So that's why I always keep the targeted identification in place, and then we can follow the mass accuracy through the results. If you do it like this, there is no tracking of mass accuracy. So I keep it on, and we select 60, and then we go to components. So just work down this list here on the left side. So here we have, you want to call it SMX, and then the formula is what we wrote down, C10, H11, N3O3S, right? And it calculates for us the MH plus, the accurate mass. And basically that's all we have to do on this page. We don't know the retention time yet. We will use the integration to find the retention time. So we can go to integration, and hopefully we see a peak. Yes, we have a peak right there. A little bit early in the run. I would not expect so early, but okay. What solvent did you inject these in?
What solvent?
Yeah.
50% methanol and 2% folic acid with silicon carbon.
So it may be that concentration of methanol is just a little bit too high, and the compound is not binding to the column. It's going straight through the column. So you may want to reduce, in order to move this peak, let's say, more onto the chromatogram, you may want to reduce the percentage of methanol in the final injection solvent, in the injection vial, maybe down to 10%.
10% methanol and 60%
Yeah.
Okay.
Yeah, 10% methanol and 90% water.
Yes.
Yeah, okay. So if you have solubility problems, you can still dissolve your compound in methanol and then just make the final dilution. Let's say from, you have a stock maybe that is 1 microgram per mil, that can be in methanol, and then make the final dilution to the 1 to 100 nanograms per mil, make that final dilution in your 10% methanol. And that way, at low concentration, your compound is probably still soluble, but the liquid in the vial is better for the chromatography. Because this maybe is a little bit early. Anyway, we'll see. Okay, so we didn't talk yet about any of these parameters, right? Is that correct? Okay, so we better do that now. So we have a nice peak, actually, nice peak shape. The only thing that I'm a little worried about is it's a little bit early, but we'll see. Maybe it's okay. All right, so the first part of the method here is about finding the retention time. So you have typed the retention time here. If you want to change it for some reason, you can type here, and it will change after you press apply. Or if you don't want to type, you can just click and drag across the peak. So in this example, we have only one peak. It's really easy, right? But in some examples, you may have more than one peak, and you have to choose which one is right. Yeah. Well, keep in mind, you don't want to build your method from an unknown sample, right? You want to build from a standard, yeah. Now we have retention time half window. So that means that the software is going to search for this compound plus or minus 30 seconds from the expected retention time. Now you may say that's a lot. I tend to agree, so we may reduce that. And now you have a choice whether you want it to report the largest peak, or if this is unchecked, report the closest peak. So we have 0.87 is here. Right now, it's going to report the closest peak it finds to that retention time. If you change it to largest peak, it will find the largest peak within that window, in the plus or minus 10 second window. So it's up to you which you choose, and also it depends a little bit, I guess, about the data. How is your data looking? Is it nice and clean like this, or do you have interference? All right, so that's the retention time. Now we have the integration section. So this is how the integration happens. Mostly what we are concerned with is where the start and the stop of the integration is. So where is this point? Where is this point? The first three settings are filters: minimum peak width, minimum peak height, and minimum signal to noise. So the peak has to be bigger than these settings in order for it to be integrated. So this is a good way to filter out small rubbish peaks that may come from your data from background noise. For example, if you see here, here's the background. And so by setting this value, the minimum peak height, to be right around the background, it will not integrate these small peaks. So we could put here, for example, maybe increase that to 150. And then we will not get a small peak integrated down in the noise. And you may want to come back and to change these later once you have looked at a blank as well. Because right now this is a standard, obviously, so it has a huge peak. So those are filters that you can use to remove smaller peaks, those first 3 settings. Now the next setting is smoothing, and what we say is that the smoothing to be used should be the minimum smoothing that you need in order to either get a nice peak or to remove any noise or anything like that. So right now it's 0. So look what happens when you have your height. I'll put it to 1. I'll say apply. So we have 4.6 E4. So now we went down.
Yes.
So smoothing makes maybe a nicer looking peak, not that much nicer, but we lose height. So every time we do a smooth, we lose some peak height. See that?
Yes.
So we want to use the lowest smoothing that we can. So let me ask you a question. If you have to use smoothing 3 or 4 in order to get a good peak shape, what is something that you can change in your data? How can you change? Pardon?
The concentration of the standing.
Okay, yes, right, that's yes. Okay, but let's say that you need to work at that concentration. That is the biological level, and you cannot change that. But yes, you are correct. You could increase the concentration. Think about from a method perspective, from an acquisition method. Anybody have an idea?
Acquisition time. She can change the acquisition time.
Acquisition time. Okay, which acquisition time? We talked about a lot of different times, right? You remember? So what is smoothing actually doing? Smoothing is
the number of data points.
Exactly, the number of data points. That's the time we need to pay attention to. So that is done by scan time or by cycle time. I don't think I can show you right now because I cannot change the mode. Yeah, but we'll come back to it and I'll show you. So if you have to use so much smoothing to get a nice peak shape, your data points are not correct. And then what you need to do is you need to go back to your acquisition method and you need to adjust your time that you have for your data points in order to get either more or less data points. And smoothing can go either way. You can have too many data points. If your peak looks very noisy, you may have too many data points. So definitely going and changing the cycle time and the accumulation time to adjust your data points is the way to then avoid using smoothing. So we can even go to fractions. So let's try maybe 0.5. Anyway, here we have very good data points. So we don't need to worry too much about smoothing. So that's smoothing. Just use the least you want. Everyone wants to use smoothing. No, smoothing is actually bad. In order to avoid using smoothing, you should collect the best data you can. So go back and to change your data points. All right, so now we have 3 settings which are going to define the start and the stop. The first one is about the noise. It's not so effective in adjusting your start and stop, especially if you have, let's say, good noise. This is good noise. Why is this good noise? It's relatively stable. It's the same before and after the peak, and it's not very high at all. 100 is really good. So the noise percentage is taking, it's basically making a new noise by taking a certain percentage of the noise points. So what does 40% mean? It means that it's taking only the lower 40% of the noise points and using those to calculate the new noise. So the software, so what does that actually mean? The software goes through and it assigns each point, each data point, is it noise or is it peak? And then all the data points it assigned as noise, it then takes the lower percentage, whatever number you have here, the lower percentage of those, and then that is the real noise that it uses to find the difference between the noise and the peak. So right now it's set to 40. Usually I leave it on 40. I don't see really a need to change it unless you find that the noise is either unequal on either side of the peak, or you have very high noise relative to your peak. But in this case, there is no need to change it. Baseline subtraction window has a big effect on the start and stop. Now this peak is really quite perfect, so it's maybe going to be difficult to illustrate it. But the baseline subtraction window, you want to set that to be approximately the width of the peak at the base. And then the software will use that peak width as approximately the start and stop of the peak. So it's at 2 minutes now, which is really not correct. So I will set it something like 0.2. 2 minutes is crazy, right? The default is a little bit crazy. I'll set it to 0.2 and I'll say apply. And now we can see, I think, that little extra bit will be not integrated. It still is integrated. I thought we could maybe reduce this little bit with it. We could go a little bit lower. Let's say 0.15. Yes, now I think it did it. Yeah, do you see that? So it changed now to there. So you are setting approximately the width of the peak at the base. That's baseline subtraction window, and it's actually your personal preference what you want to do. So if you like to have that integrated, it's not, no one can say wrong or right. As long as it's done equally on all the samples, it will be okay for the quantitation. Personally, I like to remove this kind of tailing. Now, peak splitting is really only of interest if we have peaks that are close to each other. So I will use the paint here to draw that. We still, here we were talking about deconvolution, I guess. Okay, new. So what is peak splitting? So here we have a chromatogram. So we have time, and we have intensity. And let's say we have some isomers that we just separate just a little bit, right? So what peak splitting is doing is, do you want to split that as one peak, or the other peak, of course, if you change the retention time, or do you want to integrate it as one peak together? So do you want two separate peaks, or do you want one? Basically, what you are defining is, if we look at the data points, you are defining how many data points need to be in this valley. So by increasing the number of data points that need to be in the valley, you are making it more together. So a higher number brings the peaks together, and a lower number separates them. But this only has an effect if you have that kind of peak shape. Here, obviously, we don't have, right? Here we have a very nice shape. So just remember, when you have that case, if you increase this number, they will be lumped together, and if you decrease it, they will be separate. So that's the integration parameters. We will be able to change those when we get to the chart as well. These are the defaults for the method. And if you have a long list of compounds here and you just change them once, you can use this box, checkbox, to apply these settings to all your compounds in the list. In this case, we just have one, so it doesn't really make a difference. And then the last part of the integration is the units and the calibration. So you have here concentration. So I'm not sure, what do you like to use, ppb, or you like to use nanograms per mil?
Okay.
ppb, okay. So you can type here a concentration unit. The instrument does not understand what that means. It's just a text. So I could actually type my name here. It's just the units as a text. It doesn't understand what is concentration actually. So just keep that in mind. You're not going to then be able to get, like, it won't do a calculation in ppm or something as a conversion. No, it doesn't understand. It's just a text. The regression parameter that we use almost always is area. I really didn't see anybody use height in LCMS. So area is the integrated area. Regression type, you have a lot of options. What I usually see people using is linear. And if they have a larger concentration range where the linear is maybe not possible anymore, you can use quadratic. So linear and quadratic will be, linear and quadratic will be your two main choices. And then as a third choice, you have the option linear through 0. This is interesting if you want to make a single point calibration. So usually people have a calibration curve and they have several points on their calibration curve, like you set up. But if you want to make a calibration curve with just one point, then in order to make the calibration line, you need to have another point, and that point will be 0. So it will go through 0, 0. So a single point calibration is possible if you change the weighting, if you change the regression type to linear through 0. So we'll leave it on linear for now, and that's, I'm guessing, 99% of the time you will use area and linear. Weighting. Weighting is how much weight the concentration points have in producing the regression. So you can think of that as the power of the point in forcing the line through the point. So basically 3 choices to use are none, 1 over x, and 1 over x squared. So none is good for small ranges of concentration. As you start to increase the concentration range, so you have a wider dynamic range of your calibration curve, you may need to use 1 over x and 1 over x squared in order to get good linearity at the lower concentrations. So 1 over x takes a very small concentration and makes it 1 over that. So it's making it the inverse, a much bigger number. And then the lower concentration points have more power a lot. So that is sometimes necessary in LCMS data, and it becomes more necessary with the bigger the calibration range is. We can also look at this when we get to the calibration curve, and we can make a decision which weighting is better once we see the calibration curve. That might be easier. So I'll leave it over 1 over x now, which is the default, and then we'll play with that when we get the calibration curve. All right, so those are our parameters. Keep in mind, you are not actually doing the integration here, right? This is setting up the model of the settings that will be used to integrate all of the samples. So any questions on these parameters? Everything straightforward. All right. So library search, we will not, oh, do I want to apply the changes? Yes. Library search, we will not use it at this point. Calculated columns, we can come back to that later today, and I can show you some cool things you can do with your quantitation in calculated columns. This is a little bit like writing a small Excel program. So you can write a little program to do something with your data. For example, we might find here retention time drift. So we might write a little program that says, okay, I want to see what is my average retention time in my standards, and then I want to see what is the retention time in the unknowns, and I want to apply then a flag if my unknown retention time is very different than my standard retention. So we can do little programs like that here under calculated columns. It takes a little while to get used to this, and you have to learn how to program. But once you do it, it's quite powerful in your quantitative results. So we can decide if we do that this week or if we want to save that for January once you process some data. It's up to you. But we can definitely have a session on this. Flagging rules. Okay, so flagging rules are a bunch of different rules how we can look into our data, and we can either see things that are wrong or we can see things that are correct. This is also powerful when you are looking into a very big data set. And quickly see things that are incorrect. So let's go through them. Ion ratio, we'll come back to that later on when we talk about the swath quantitation. I saw that you ran also in swath, so we'll come back to that, and I'll show you what is ion ratio. Okay. So then we have accuracy acceptance. So what is accuracy? Accuracy is how well the standard points fit the calibration curve in terms of the standards. And for the quality controls, accuracy is how close the quality controls are to your expected concentration. So you have here some percentage, and if the accuracy is more than this percentage, it will be flagged. So right now we have 20% allowed accuracy for the lower limit of quantitation, 15% for all the other points on the standard curve except the lowest point, and we have 15% for the quality control. So that's like a check that everything is linear and everything is as expected. So we'll leave that on. Concentration acceptance is a concentration flag. So if the value for the concentration for your compound is above or below a certain limit, it will flag it. So for example, if you're looking to see, okay, I want to see is this compound, more than 10 ppb in any sample, I can put 10 here, and then it will be flagged as higher than 10. And it will give a red mark, and you'll be able to say, okay, here are my samples where the concentration is higher. I'm not sure this is so useful for you because probably you just want to know the concentration. You don't maybe have a flag or a limit. So we leave that blank for now, but you can do that. Maybe we turn that one off. Integration acceptance. So you have integration quality, and you have a symmetry factor and peak width. So these are settings where you can, or these are parameters where you can apply settings if your peak shape is not good. Integration quality is a value from 0 to 1, 1 being a very nicely integrated peak, and 0 being maybe a horrible peak shape and a bad integration. It is a random, let's say, with the unitless value that the software calculates for you. And then you have asymmetry. So is the peak leaning one way or the other? Do you have peak fronting or peak tailing? You can set up limits for that. And then you have total peak width. So is the peak less than 0.25 or greater than 0.5 in width? Now we don't have retention time tolerance here because I will show you it is also in the qualitative rules. And here are the qualitative rules, and we have here error in retention time. So what I'll do is I'll turn on the mass error and the error in retention time, and we'll also turn on the difference in isotope ratio. And if you remember, this is what I was talking about at the beginning, why we want to leave the targeted screening section turned on, because now we will have a flag for these settings. And if the mass error should drift, then your XIC will be less intense, and you will think I have problems in my quantitation, but actually you have problems in your mass accuracy. So I will just change these settings to be a little bit stricter, because we are actually looking at something very close, and I'll give the combined score 50, error in retention time. So we can set up an absolute error perhaps, and we can say, all right, 0.3 drift, and maybe 0.5, or here we could do, yeah, let's keep it like that for now. And difference in isotope ratio, okay, we'll do 20 here, we'll do 50 here. And we'll make this part of 25 of the combined score. Okay, so we will still have some checks on the quality of the data, which is important, I think, in a time of flight, something that you would perhaps not do in another system. So I'll turn that on. And then the last setting is Formula Finder. Okay, we're not going to use Formula Finder now because we're not doing any kind of unknown screening. This is targeted quantitation on this target, on this formula. So we don't need to do Formula Finder. Okay, so that's our first method we made for quantitation. Any questions on that? I will do save as, and I will say SMX 001. Everyone okay with those settings? Yeah. Then I'll say browse, and oh, no. We can wait. Yes, okay. Browse. Once those sort of, let's say, small crashes start happening, it is a good idea to restart the computer, because probably you are at the maximum memory of the software, the memory consumption. And that's also why it's maybe a good idea to set up a separate processing station so that processing doesn't interfere with the sample analysis. Okay, let's keep going and see how we do. All right, so we have now our processing method here, and we have all the data we're going to process. So we'll say process, and what we will get from this is a new chart. And here we will see the integration happening. So it's integrating all your samples. All right, and it minimized itself. All right, so here's the chart. And I think we talked quite a bit about this chart before, right? On the left side, you have the two tabs. One is all the samples, and one is all the components. So here we just have one component, so it's quite simple. Now, table settings. So we should adjust our table settings for quantitation. I believe I set you up with some table settings, right? I can't remember what we did. Yeah, we did some screening table settings, right? So let's start with that. At least it will get it in the right order. And what I will do is I'll add a few things here that we need for quantitation. So I will come to table settings, and I will play now with the columns. So we're going to need accuracy and accuracy acceptance. We don't need adduct so much because we know what we're looking for. Area is important. Combined score, we need calculated concentration. And I like to see calculated concentration in a regular number, not in scientific notation. So I'll change that to calculated concentration to remove the E. Comparison, you can display the concentration units if you want. Concentration acceptance is good. Expected retention time, we don't need the formula anymore. It's not important in quantitation. Found at mass is good to keep. You don't need any formula stuff. Index, integration type, ion ratio. All right, so here we don't need the library. Not doing library search. Mass error is still important. Talked about that. Outlier reasons now becomes interesting. We can learn from the flagging what is the reason we have a flag. So the outlier reasons will tell us that. Precursor mass we don't need. Reportable, retention time confidence, fine. Sample name, sample type is important. And used. Okay, so I will say okay. All right, so here's our new chart with the new layout. I'm going to move the accuracy acceptance. So I have all my flags in the same place. Okay, so we have sample name, we have the flags, we have the sample type. We're going to talk about that in a second. We have the component name, concentration units. We have the outlier reasons. Outlier reasons, I'm going to put way over here on the side, so it's like a comment. All right. Expected retention time, I will put next to retention time. So we have area, expected retention time, we have the difference, we have the calculated concentration, we have accuracy, found at mass, then we have the mass error, we have the score, and the isotope ratio. Okay, so what I'll do is I'll save these and I'll put them in the same place as I put your other table settings, which is always under SciEX data. So there you see that. And now I'm going to call this quant TOF no ion ratio. We'll talk about ion ratio when we look at the swath data next. Okay. And I'll say okay. So now that also appears under your recent table settings there as an extra setting. Okay, so this is our first quantitative results. The first thing we just want to glance at is that the mass error is okay. So that's fine. So I might like to take a look at my calibration curve first, right? That's usually what I like to do in my quantitative results. Did I make my calibration curve correctly? So this button here displays the calibration curve. And what you see is that it's blank. So we don't have a calibration curve. And that is because at this point, we didn't tell the software yet which points are standards and which are QCs and which are unknowns. So you have here sample type. And what we have to do is to change this for each sample. And that is what is the injection. So solvent and standard. So as I do this, you can see that I start to get some points on my calibration curve below. So when I click standard, the software knows that's a standard, and it starts to plot it on the standard curve in order to make the standard curve. And the last one is the unknown. So there's all the points on the standard curve, however, they are at 0 concentration. And the reason for that is we need to put actual concentration. Oh, which I forgot. Calculated concentration, My mistake. All right, so we don't have that column visible. So we have to come to table display settings, and now we need actual concentration. There we go. So it put actual concentration right here. So maybe we can move it next to calculated concentration, and we can put the concentration units here. Okay, so let me save that layout now. And you have a good layout for quantitation, QuantOff, no iteration. Okay, yes. All right. So what we have to do is we have to fill out the actual concentration with what is the concentration. So you did it very nicely. It's in the sample name, right? So you see as I'm typing here the concentration, then the standard curve below starting to form correctly. Good. All right, so there we have a truly excellent calibration curve. So that's really nice, lovely, huh? So now you see we have actual concentration that assigned each one of these area points, right, to the correct place on the x-axis. And then automatically the curve, actually the line is drawn, and that is then applied to the unknown. So here's the unknown sample. The unknown sample, we cannot type an actual concentration, and the calculated concentration is given here, 62.1 ppb. So that is, in a nutshell, how the quantitation works. You have actual concentration is for the standards and the QCs, and calculated concentration is the result. So you would read for your unknowns the result from the calculated concentration column. All right, now we can go, of course, a little deeper and we can see what's going on. So we have some problems, and those problems are shown to you in the red color. Now, also what we can do is we can view the peaks themselves. So we can click on this button, Peak Review. We use this when we did the screening. And now we are seeing 2 peaks. So what you can do is you have quite a lot of peaks shown here. So you can go to Options, and if you want to see them all together, you can say, for example, I want 4 rows, and I want, actually we'll do 3 rows and 4 columns. That's a little bit easier. So now I can see all the little peaks. Maybe that's too much for you. You can use the truck tire, move it on the side. There's the red bar. So, and we can move this up. And we can move this over. Great. All right. So definitely, I urge you to play around with the display and to get a display where you can see the data easily and nicely for your needs. That's makes life much easier than having to scroll and to look at multiple windows and so on. All right, so here are the 12 peaks of the standard curve. So just to remind you, right, I did that under Options, Peak Review, Display Settings. Under Zoom, oh no, here under Appearance, you have rows and columns. And under Zooming, you have how much you want this to zoom in on the peak. So definitely you'll have to set these 2 settings here, these 2 tabs, for your different data. Okay, so we can see the integration is nice. And actually, in terms of the peak shape and so on, everything looks pretty good. The 1 ppb is roughly the bottom end, right? So we are starting to suffer here a little bit from sensitivity. We couldn't go too much lower than this. This peak, maybe we don't want it to be a peak at all. So here we can adjust our minimum peak height. I will make it 300 actually, 300. And then we'll say apply. Now you see that peak is not integrated. So the blank is showing no peak. So of course that's up to you how you want to set that. I prefer that these really tiny peaks are not integrated. So we got rid of some problems there. So we do have some isotope problems, and that will happen at lower concentration. So at lower concentration, there's probably some interfering masses that affect that. I wouldn't worry too much about that, as long as you have a good XIC. Keep in mind the isotopes are the other peaks, which are less intense. So they are even less intense than the XIC we are following. So you may see some isotope problems at lower concentration. And then you have accuracy acceptance. And if you hold the mouse here, then you can see that the accuracy failed because these values are out. So this one is only just out. We have an allowed tolerance of 15%, and this one is quite far out. So here's a case where we need to apply the weighting. So right now we have weighting 1 over x. We zoom in here. Let's zoom in and take a look at these lower points. You see the lower points don't fit the line so well because they don't maybe have enough weight. So what we need to do now is we need to balance the weighting with the accuracy at each point and the overall linearity. So here you have your R and your R squared values, which tell you how linear the regression is overall. So what I'm going to do is I'll change it. Come here and I'll say 1 over x squared. So now pay attention to the accuracy numbers and the R numbers. And we'll see what happens. So I'll say okay. And there we go. Now we have accuracy improved, at least for the lowest point. For this point, it got a little bit worse. And the R value also got a little bit worse. So you have to balance this with your work. Do I want to have more accuracy at the lower points, in which case I'll increase the weighting and I will affect the R value overall? Or do I not care about the lower points and I can go back to 1 over x? And now I have bad accuracy at the lowest point, but I have better linearity overall. And I may decide, okay, actually 1 ppb is not reasonable for me. So I can even right-click and I can say exclude. Right? And now it drops out of the calibration curve. So actually it's not even used in the calculation of the regression. It is still in the chart and you still do have an accuracy issue here because it is still marked as a standard. Even though you are not using it, you see the used box has gone away and it has now an open dot in the calibration curve. So maybe for this compound, 2 ppb is the limit of quantitation as we have it right now. And the weighting 1 over x gives a nice balance of accuracy at every point versus linearity. So if you want to go to 1 ppb, we would need to do something perhaps to the acquisition method in order to make it more sensitive overall, rather than try to force that point to fit on the curve. So we could, for example, increase the injection volume. Maybe if we change the injection solvent a little bit better, matching the start of the gradient, the peak might be better. We could also play with the voltages and the source parameters and so on in order to try to improve the sensitivity of this compound. So there are quite a few things we can do if we need to get the 1 ppb on scale. All right, so everybody okay? Following? Everybody understand? Any questions? All right, so given your unknown sample is quite high concentration, I would leave it like this and just remove the 1 ppb. Unless you really need to do accurate quantitation down here. Look at the calibration curve anyway, we're very accurate down to 2 ppb, right? Because even at 2 ppb, we have 96% accuracy. So that's pretty good. Okay, so what can we do further now in the quantitation? I can show you a few other things that we can do. And then perhaps we will take a break, and then we'll come back this afternoon and look at the swath data. And maybe we can decide overnight to run some more tuning experiments if we want to improve this 1 ppb point. We can decide to do that or not. All right, so the next few things are a little bit detailed, but we'll just kind of go through them, and I'll show you how it works. So do you remember we made the change here? We changed this minimum peak height, and we made it 300 to exclude that. When we changed that, we changed it only for this one injection in the blue box. You see, if I go to another injection, it's back to 150. So let's say I made it this change, and I want to apply it to all the injections. What I can do is I can right-click, and I can say Update Processing Method for the components. And when I do that, the samples will be reintegrated, and that change will be applied, minimum peak height will be applied to all. And so now you see when I click on the other injections, it's also 300. So that applies to any change that I make. Let's say, I'm not happy with this noise here, so I want to make the smoothing one. I can change it, say apply. So maybe I like that better. But I cannot have smoothing, just one for this and half for the other points. So what I need to do again is right-click and say Update Processing Method for Component. Now it will change the processing method for all the components, and it will recalculate. So now if I do on another one, you see it's also smoothing of one. Didn't fix much. Huh? Still, we don't have great accuracy for that point. So that point is really, I think, below the limit of quantitation. So in this case, I'm probably hurting the other data, so I may put that back. 0.5, apply, right-click, and update processing method for component. Okay, so in this way, you see I'm still working a little bit on my processing method when I'm actually in the data. And I'm making changes now based upon the quality of the data that I see in the chart. So now there's a little trick. I made these changes in the processing method. If I want to apply these changes and use them for other data, I have to get the processing method out of the chart. When you make the chart, every time you make the chart, you get what's called an embedded method. And if you look up here under processing method chart, you have here edit the embedded method and save. You are not affecting the method that you actually saved with a name at the beginning. You are affecting only the method that is embedded in this chart. So in order to get this change out, we made two changes, right? We adjusted the peak height to 300. Oh, we changed the Gaussian smooth, but then we changed it back. So actually, we only made one change. So we can do save embedded method as, and now I have here the SMX1. I have the chance I can override it with my new change, or I can give it a new name. And this is essential to use the change that you made, or changes that you made, if you want to process other data now with these changes. This is a little tricky for some people. They work on their data and they update everything, and then they go to process new data and they realize that their changes are not there. So you're not actually affecting this method until you come back and save it like we are doing now. Save. Then it will ask us to replace. Save. Come on. I didn't ask replace. Or maybe it did and I didn't see it. Save embedded method. Here. Save. Okay, that's a little strange. Usually it says it already exists. Are you sure you want to save as? And then you can say yes. Anyway, so now we have overwritten that method with our change. Okay, so we talked about how to remove a point from the calibration curve. Right click. If you want to put it back, you can right click and say include. And now it's solid. And you can do that for just this analyte, or you can do it for all analytes. So it means remove that whole injection, basically. So that injection will not be present for any of the analytes. And we already talked that we can save the chart. So under results, we can say save as. All right, so then I'll say this is SMX QTOF only. And I'll put training. I think after this session, we're also going to restart the computer because it's very slow. Is it also going gray for you in the lab?
Yeah.
Oh, that's not a good sign. All right. So you can remove any of this windows that you need, and to bring it back, you just click the button again and it comes back. So now in the peak review, we looked only at the XIC. So under view, we have XIC. If you do want to see the MS, you can change it to MS. And then you have, again, options, peak review display settings. Maybe for this, it's better to just have one row. And here's the peak, and here's the mass spectrum. So that is why we have that isotope, right? Because there's, look at that, that's the mass that we're using to calculate the XIC. So that shows you the sensitivity. I wish that Tony was here to see that, because that would really show you how sensitive the system is, right? Look at this. This is actually a decent XIC. Okay, it didn't fit on our quantitation curve, but that is the parent ion that we are looking at in order to get this XIC. And for me, that's quite amazing. If we look at 2 ppb even, so this is really good quantitation. This is on. There's the ion, right? It would very, very hard to see that if you were looking for it without knowing anything. But because we're doing targeted analysis, of course, we can find it, and we get really excellent quality data on 2 ppb. So that's what the instrument is designed for, high sensitive work and ionization of so many things. So I just wanted to show you that. That's why we have bad isotope, because that's the monoisotopic. Where is the isotope peak? The isotope peak is in here somewhere. Let me zoom in. Zoom in. So there's the peak, and the isotope is, and we even see it. So it should be at 255. It should be right here. Yeah, there it is, right? There it is, right there. So down in the noise. So that's why we have the yellow, and it's even yellow. It's not red, right? So it's kind of okay. It's within kind of, you know, we need some interpretation. So that shows you the power of the instrument. Okay, so to go back under view, go back XIC, now we see just one row. So if we want our 3 rows back, come here, 3 rows. Okay, so there are 2 more things I can show you in the quantitation software, which are little tools that you can use to help you. The first one is kind of easy. It's the statistics. So I will close the peak review. And under views, we have statistics pane. Now for peak review and for calibration curve, you have the buttons here. But for some reason, there's no button for statistics. So you have to come under view and say statistics. And this pane shows you now statistics. Now in this case, we don't have multiple injections. So we cannot generate statistics from a single injection. But here you have all of your standards in the list. And you can use this menu to group them by concentration, or you have the option to group them by name. So it will either group anything that has the same name or anything that has the same actual concentration. You see right now we just have one, and then it tells you the mean, the standard deviation, the percent CV, the accuracy, and also the values. So you have automatic statistics calculation here, also by name. You can change it. And then you have in this menu, you want to use, oh, sorry, one more thing. Here at the bottom, you have it for the QCs. So you can also change to look at the statistics for the QCs if you do multiple injections of your QCs, concentration for the QCs. We don't really have any QCs right now, so they're not in the, it's not showing anything. And then here we can adjust which parameter you're looking at. So are you looking at calculated concentration? Are you looking at peak area? Height is not so useful, I guess. And calibration Y value would be if you have an internal standard. So that's also something that I can show you, is how to use an internal standard. Okay. So we can do that as well. So the calibration Y value then takes the Y axis of your calibration curve. In the case of area, if you're using area, it's the same. If you're using an internal standard, then it is area ratio, which is the ratio of your analyte divided by the area of your internal standard. So that's the statistics pane. Just remember it's under views and then statistics. All right, so the last thing I want to show you in the chart is how to make something called a metric plot. So what is a metric plot? A metric plot is a way to make a chart or a graph, to make a graph of any 2 variables in this chart. So we can take 2 variables and we can plot them on X and Y, and we can then visualize any, you can visualize any relationship between them. So let's say I want to see retention time for each sample. So I will make a new graph, a new metric plot, and this graph will have injection number on the x-axis, and on the y-axis it will have retention time. And the idea is to check, is my retention time stable over time? So the way that I do this is the first column that I want to be on the x-axis, I will highlight it first. That will be the x. And then I will press and hold the Control key, and I will select retention time. That will be the y. The second column that I select is the y-axis. And then under More, I have here Create a Metric Plot with New Settings. I make the metric plot, and now you see we have exactly what we selected. On the x-axis is index. So this is the index. Basically, it's injection number index. And then on the y-axis, I have retention time because I selected here retention time. Now I have the blank. The blank has no peak. So what I can do is I can use the funnel here, and I can say, all right, I don't want to see solvents. I only want to see my unknowns, my standards. Now it disappears from the chart. It is not visible anymore. And you see I have the funnel here selected blue because I'm using the filter to remove some data that I don't want to see. It's not removing it from any calculation. It's just removing it from your visual, from your view, removing it from your view. So now we have a chart, and actually there looks like quite some variability here. But what you can do is you can apply also statistics in the metric plot. So we can do a few things. We can say options. Maybe we want to start the y-axis at 0. That's also helpful. So now we see, okay, this is 0, so it kind of normalizes a little bit better. And I have the chance also to add some regression here. So I can do regression. So let's say, what should I do? I'd like to do mean, I think. I want to see the average retention time. Mean retention time. And I can include some deviation lines, okay, with 2 standard deviation multipliers. Or I can do 1 or 3, whatever I want. Okay. And now you can see, actually, even though when we had it set not to view 0, it looked like there was big variability in our retention time. Actually, our retention times are within 2 standard deviations of each other. So actually, there's not much drift in the retention time. That's pretty stable. So you can use this metric plot to plot any 2 variables that you want from the chart. Just always remember the first variable is the x-axis. So if I highlight index, I will get that on the x-axis. And then I press and hold Control. So what else can we do? For example, we could do mass error. And that'll be on the y-axis. Then I say More and create the metric plot. Now I have a metric plot of injection number versus mass accuracy, mass error. And I can say also some statistics if I want. I can start the y-axis at 0, although that's not really going to help because I have negative numbers in this case. So I can say regression. Okay, so do I want to take the mean? Yeah, I can take the mean, and I can say maybe here are 2 standard deviations. So we can see any drift in the mass error. Now this one is not used, and that is the very low peak, which also, it has a mass error actually of out of the spec. I set the green to be 3. Maybe I should set the green to be 2, because everything that is correct is really within the spec. So how can I edit that method to change that setting? I can go to Process Method, and I can say Edit, and now I'm back here at my main method page. So I can change the flagging rules, and I can say qualitative rules, and I can make my green 2. And then I can say process and close. Notice there is no save here. Process and close, right? So I have not changed the actual processing method that I made at the beginning. I've changed only the embedded method. And if I want to accept that change and save it to use it again, I have to come back to process method and say save embedded method. And now I have the chance, okay, I can save it with this name. And now that change will be there. So there it is, right? Mass error is now yellow color because it's between 2 and 5 ppm. So maybe that's a little bit better
تحط استرال بالصندوق استرال
to visualize, okay, something is going on there. I like that better, actually. Okay, so let me show you about the internal standards, and then we'll open it up for questions, and then I think that's the last thing we'll do, and we'll take a break. And then when we come back after the break, we will do the same thing again, but we will process the swath data. And I'll show you how to incorporate the fragment ions. And then we can talk about ion ratio, and we can talk about which way to do quantitation is actually better. Is it better to do it from the TOF MS, or is it better to do it from the swath? So we'll have a little comparison. And that will also be able to compare the sensitivity of the instrument in both modes. So I think that's useful for everyone. Okay, so how do I use an internal standard? An internal standard will be applied in the processing method. So we'll go back to edit our processing method. And under components here, I have the IS column. So IS column needs to be checked if the compound is the internal standard. So I'm not sure, we'll just make something up. So we'll say like XXX. And also it has the formula. I think I showed you how to do the stable isotopes. Did I show you that? So let's say you have, we'll use a real example. Let's say your internal standard is SMX D6. What does the D6 mean? It means 6 deuteriums. Maybe I should ask everybody if they understand the concept of stable isotope labeling as an internal standard. Does that make sense to everyone? Does everyone know about that? Yes? No? Maybe.
Can you explain what this means?
Say again, a little bit louder. I couldn't hear you.
Can you explain what does this mean?
Okay, yeah. So I'll go to the web. So basically, yeah, this is what I want. So basically, we have the structure here of the compound. What is that called? Snip or something, right? Yeah, snipping tool. So I'm just going to grab a picture, and then I'll use the paint. Okay, so this is the structure of your compound, right? And where's paint? And we'll say new. No. All right, so this is your compound. Can we make it bigger? What happened? Weird? Okay, well, I'm not going to play around. Okay, so here's the structure of the compound, right? Now, what do I want in quantitation? I want to be extremely accurate and extremely precise. So one way that I can improve my accuracy and my precision is that I can add what's called an internal standard. An internal standard is something that I add usually at the beginning of the sample preparation, although not always, but usually it's added as the first step. And then once that's added, the ratio of that compound to my real compound is fixed, right? So if I lose a portion of my sample during the processing, then it doesn't affect the ratio. It will affect the intensity, but not the ratio. So what makes a perfect internal standard? Well, something as close to your compound as possible. And the best kind of internal standard in mass spectrometry is then the same compound, but some of the atoms have been replaced with deuteriums. For example, some of the hydrogens replaced with deuteriums. or the carbons have been replaced with C13, or the nitrogens have been replaced with N15. These are stable isotopes. If you remember back to when we had the lecture, we talked about stable isotopes, right? They are the same physically, they are the same chemically, but physically they are different by the number of neutrons that have been added. So let's say I have this hydrogen, or let's say I have here, then I will put what's happening. Oh, man. I'm not doing very well in paint today, am I? Okay. So I want paintbrush and red. Okay, so let's say here I have a deuterium, and here that will not have a deuterium, sorry. So here I can put one deuterium, right? So I'm taking these hydrogens and I'm replacing them with deuteriums. And this is not something that we can do in the lab. You have to buy these, right? These are compounds that you buy. So where is another deuterium? Actually, that's all really I can see easily. Okay, so we have D5, right? So now this is SMX D5. This would be something you would buy from Sigma Aldrich or some other company. Now, SMX, it has the same chemical properties as SMX-D5. So when it's in the sample and the sample preparation, it will behave almost identically chemically. However, it is plus 5 Daltons, right? So we will be able to distinguish in the mass spectrometer the difference between the SMX and the SMX-D5. So that's why they're called stably isotope labeled compounds, or sometimes you hear it stable isotope labeled analogs. These make the best internal standards for quantitation in mass spectrometry. And they behave identical to the real compound, except they are heavier, and in this case by 5 deuteriums. So hydrogens places have been replaced with deuterium. So, does that make sense to everyone? They also happen to be the most expensive compounds, even though they are the best. So we will make here, I can't type, SMX D5. So what will that be? It will have 10 carbons, and now it will have 6 hydrogens, and then it will have hydrogen 2 is deuterium, H2, 2 deuteriums, and it will have 5 of those. So that's the deuterium, and then the rest of it is the same, N3O3S, right? And the software knows that, so you see it's 5 Daltons heavier. So we set it up as an analyte, just the same as the other analyte, except we tell the software here that it is an internal standard. Now it knows, okay, that compound is an internal standard. And then the second thing we have to do is we have to apply that internal standard here under IS name. So it means SMX, its internal standard will be SMX D5. Now both compounds will be integrated the same way. Now we're not going to have a peak for the D5 because you didn't add it, which is fine, don't worry. But so you see here, I'll just go through the example. Here now you have the 2 compounds and they are integrated separately. So obviously there's no peak for D5, it's okay. We didn't add it, so it's not there. But they are integrated separately and the peak area is calculated for them separately. So I'll just say process and close, but I won't save anything. And now all the quantitative results are roughly the same, except you see you have an internal standard here. And for each analyte, you have also its row with internal standard. So of course, we have a lot of colored icons now because the internal standard is not present, so it doesn't really know what to do. But the big change is in the calibration curve. Now you see here on the y-axis, you have, instead of area, you have area ratio. So it is taking for each injection the area of the analyte and dividing by the area of the internal standard. And the reason for that is because we added the internal standard earlier in the sample preparation. We set the ratio at that point. So now we need to look at the ratio and not the individual area for each compound. So that's how to use and how to apply an internal standard in your work. Everything is still the same. You still read the answer from the calculated concentration column for your unknowns. And everything else we talked about is the same. You can still remove points from the calibration curve. Right click. You can still do the peak review. So we can still see our peaks. All of the process of the quantitation is the same, except for we are now looking at area ratio rather than area. So does that make sense? So probably you're thinking, do I need to use an internal standard? Well, it's hard to answer that question. For sure, you will be more precise and more accurate with an internal standard. Whether you actually need to use it or not is really dependent on, I guess, the samples and how complicated the sample preparation is and how likely you are to introduce some variability in your procedure. What you can do to test it, if you need to use it or not, is to make some control samples, right? So you can take whatever sample this is, and you can spike in the compound before the sample preparation, and you can spike in the compound after the sample preparation, and you can run those as separate samples, and you can compare your peak area. And if your peak areas are all okay, you don't need an internal standard. If your peak areas are vastly different, and especially if then you produce several samples and you spike the same amount and you get vastly different areas, so you also need to test reproducibility, right? Or precision. Precision is reproducibility. And your areas are different from the same sample prep, same concentration, then an internal standard can be valuable for you. So it's hard to say whether you actually need to use it or not just by thinking. You actually have to do it and kind of see if you need it or not. Now, does your internal standard need to be stable isotope labeled? That, like I said, that's the most expensive kind of internal standard. Maybe you can find another compound which is similar, different mass, of course, needs to be different mass, right? Because it has to give a different signal in the mass spectrometer, maybe different mass, but behaves similarly. So you're interested in SMX, right, which is sulfamethoxazole, right? So there are many similar sulfur-containing antibiotics, right? So I think if we just go here to sulfonamide, yeah, right? So you may choose one of these other compounds, which then will behave somewhat similarly chemically, but different mass. So and obviously that you're not interested in measuring, right? You cannot add something that you're interested in measuring. So you could use that as a potential internal standard if you need to. Does that make sense?
Yes.
Yeah? All right. Okay, so any questions on basic quantitation? So this data we use time of flight scan, we use the TOF-MS scan. I think that under normal conditions, So like daily use, this will be the most sensitive scan for quantitation. As you know, there's no MSMS here. So we're not taking any instrument time and using MSMS. In quantitation, the MSMS could be useful, but maybe not. So I think in terms of sensitivity and number of data points, the TOF-MS scan will be the most sensitive. But what we can see, well, I think we'll take a break now. We've been going at it now for a couple hours. So I think everybody would appreciate maybe a little bit longer lunch break. We'll take a break, and then when we come back after the lunch break, we'll look at the swath data and we'll compare. Just before we do that, I would like to, I recognize now that I said one thing and then I didn't go back and change it. So do you remember when we were talking about smoothing and I was asking you, okay, if you have to use a high smoothing, what is actually wrong with how you collected your data? And one person said number of data points, which is actually exactly correct. And another person said about the time of the method. That's also correct. So I'll just go and show you where that is, right? So here under MS method, what we can do is we can open our method. So I will open the TOF MS. So actually, I don't remember which one we did. I guess we were doing 25 minutes, right? Because we made the gradient a little bit longer. Anyway, where is the setting, right? Here is the scan time. So, but you can't change that, right? It's fixed. The scan time is 0.527 seconds. That means we get a data point every 5.27 seconds, roughly half a second, right? So 2 data points per second. So if you need to change that because your peak shape is not good, meaning that you don't have enough data points to define your peak, then you have to change this. But you can't change it here. So where do you change it? You change it here, right, under accumulation time. So you set the accumulation time, which is the amount of time for each scan. And then the system calculates the scan time, and you see there's a little bit of extra time. And that extra time is needed to prepare the instrument between the scans. So let me ask you a question, and you guys can see how you can answer it. So let's say I need to have more data points. This is my method. I have a scan time 0.527 seconds. I've processed some data, and I've looked at it, and I've decided my peak shape is not good. I have basically triangle peaks, and I would like to get some more data points. What do you think I should do? Should I increase the accumulation time, or should I decrease the accumulation time? Not everybody answer all at once. Yes? What? I didn't hear, sorry. Decrease. Yes, decrease. So if I decrease, for example, 0.25, right? Now I have a scan time of 0.277, and now I will have 4 data points per second. So it means I will have more data points. So this is the relationship between the accumulation time and scan time. And this is definitely something that you will need to do, especially in a quantitative method, is really to make sure that you have a good number of data points. So everything is okay for us now, so we put it back. I won't save, but I will open, for example, the swath method. Let's take a look at the swath method together. So here's the swath method. You have the same thing, right? Total scan time is up here, but now you have 2 accumulation times. You have the amount of time for the TOF-MS plus the time for the MSMS. So you will need to, when you're doing quantitation from the swath method, you will need to take into account both of those times in order to affect this time. This time is the sum of both of these numbers. So now you see, okay, if I'm using the TOF MS for my quantitation, then in the swath method or in the IDA method, I have all of this extra time for the MSMS, which maybe is not necessary. So here we're using 90 milliseconds only for the TOF MS. In the TOF MS only method, we have 500 milliseconds just for the TOF. So you can imagine the TOF MS will be more sensitive than the swath MSMS. And I think that will be our discussion points for this afternoon. Does everybody remember how to see the data points? So remember from analytics, you have this button. I think I showed you this button, right? Open data exploration. This opens the data that you're looking at in analytics. It opens it directly in explore mode. So when we click that, there's the XIC that we're looking at in explore mode. And do you remember how to visualize the number of data points? You have under window, you have graph selection window, right? I think we talked about this, yes? And then you have this button. And this button shows you the number of data points. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You have about 15 data points there. 12 to 15 data points. And that's perfect. Anything greater than 10, let's say between 10 and 20, with a target of about 12 to 15, is really excellent. So when you're building your quantitative methods, you want to come and to check this and to see that you're in the right range. And then if you're not, basically stop your data processing because your data is not going to be any good, and go back to your acquisition method and adjust your times and rerun until you have the right number of data points. And I guarantee you, if you have the right number of data, if you have the right number of data points, the rest of your quantitation will be much easier because all the parameters that you need, such as precision and accuracy and so on, will all fall into place. Does that make sense to everyone?
Yes.
Yeah? Yes. All right. So shall we take a break here? We're a little earlier than we said, 20 minutes earlier. But I think we covered a lot of things this morning. Take a little bit of a rest, and we can meet back. You guys are the same time as me, right? It's now 12:10 for you?
Yeah, correct.
Yes, okay, right. So shall we meet back at 1:30 then? And
Sure.
1:30, we'll go through the same exercise again, but we'll use the swath data, and I'll show you how to incorporate the fragment ions in the quantitative work. And this will be very interesting because we'll talk about MS versus MSMS quantitation.
Okay, great, perfect.
Good? Okay, super. Okay, guys, so have a nice break, and I will see you again at 1:30.
All right.
Okay, bye for now.
Bye.
A little bit better in terms of accuracy. But we don't see the biggest advantage, which would be the selectivity if there was high background at the time of flight. And we still have the bad, not so great mass error there. So it's hard to show you the difference because the data quality is so good. But if you had high background or some interference, this would be possibly cleaner. So that's what I wanted to show you about swath. Now the ion ratio. Okay, so the ion ratio. What is the ion ratio? And maybe I need to set this up a little differently. Okay, so we'll go back to the process method. I'll say edit, and I'll show you about the ion ratio. Okay, first of all, I'm going to label these a little differently. I'm going to call this 1. I'm going to call this 2. And I'm going to call this 3. And I'm going to call this 4. And I'm going to turn on, under flagging rules, ion ratio acceptance. And now, here are the tolerances for the ion ratio. So what does ion ratio mean? Okay, let's go back to the presentation, and let's look at an MSMS spectrum. Let's see if we can find that bromocryptine spectrum. No, must be down, right? Must be here somewhere. Yeah, okay. So here's, no, not bromocryptine, busperone. Here's busperone MSMS. So you remember when we were talking about the MSMS spectrum, we said that this spectrum was the fingerprint of the compound. I even put a little fingerprint there. And why did we say that? Because this pattern is conserved from the structure of the compound, right? It will always give a 1-2-2 because that is the weak point of all busperone molecules. Every busperone molecule will fragment in the same way. So this pattern is conserved for all molecules of busperone, and it is its characteristic. So we said we can do library searching, right? We have a library, and we can search all of these daughter ions against the library, and we can get a nice match. Now, when we do quantitation, we don't have full scan information. We just produce the XICs. So the first XIC we made was for the parent only in the TOF-MS, and now we added other XICs for the different daughter ions. Well, those XICs come from this fragmentation pattern. So what we can do is, if this fragmentation pattern is the fingerprint, we can look at the relative ratio of the areas of those XICs for the different daughter ions, and that relative area will be the same as the relative area difference of these peaks in the fingerprint, in the full scan. So if it's conserved from the standard to the sample, then it helps us to prove that the compound is correct. So that's exactly what we do with the ion ratio. We look at the ratio of one daughter to the parent, another daughter to the parent, and the third daughter to the parent. And we do that for every standard. And then we take the average ratio for the standards. And that becomes your expected ion ratio. Yes, we are talking about quantifier and qualifier, it's correct. But quantifier and qualifier comes primarily from MRM. And so this is a little bit different because we are making XICs of the daughter ions, but it is the same general idea. So the quantifier would be the XIC of the parent, and the qualifiers would be the XICs of all the daughter ions. That was a question that was asked in the chat. Are we talking about qualifier and quantifier? The answer is mostly yes, but it's a little different because in quantifier and qualifier we have separate MRMs, and here we're just pulling XICs from the same data. So if we go to OS, this is the tolerance for the difference in the ratio between the standards and the sample. So how close does the ratio need to be? So let's leave it on constant tolerance for now. So if we're within 20%, it's considered good. If it's 20 to 40%, it's considered marginal, and worse than 40% is considered unacceptable. So let's process that, and then we'll take a look at the data, and I'll show you we have some ratio lines that we can actually overlay. So now you see I turned it on. Now we have the flag here. So let's take a look what we have. Here are our peaks, and here's our calibration. I will put the, oops, I wanted to do it the other way, just because it's what I remember. Okay, and then this one, go over. And now I think we lost our actual concentrations because I didn't save it, which was not very smart. Where is actual concentration? Yeah. All right, just give me a second to retype this. 1, 2, 2.5, 5, 10, 20, 40, 60, 80, 100. Okay, and then we'll apply those to all. All right, so we now have the column ion ratio and expected ion ratio. So what is this the ratio between? This is the ratio from the 1 to the 2. And if we look at the 3, it's from the 1 to the 3. If we look at the 4, it's from the 1 to the 4. So I think it'll be easier if I overlay. So we can overlay the ratio in the diagrams, in the chromatograms. Say options, peak review, display settings. And then here, under overlay, have quantifier and qualifier with ion ratio lines. So let's take a look at this. Okay, so here we have now the overlay. Maybe I will make this a little bigger. Will be easier to see. And I think I'll zoom in a bit more. And let's also, we don't need to see all 12 now. So I'll just go to 1. I think that'll be the easiest to show this part so it's nice and big. Okay, so here we have the XIC in blue of SMX2. What is SMX2? SMX2 was the daughter of 156. And the pink is the SMX1. That is just the parent. So the ratio between those two is the ion ratio. So the area of the pink and the area of the blue, and the area of the blue divided by the area of the pink gives us ion ratio. We have this bar. This bar is where it should be. That is the expected. And then we have the range, plus or minus 20, up and down. And that bar comes from the average of everything that is marked a standard. So one thing that you see is that we have quite a big range of ion ratio, and that's probably because, yes, at the lower concentrations, the peak shape is not great. So that is affecting the big range of the ion ratio and then making the data perhaps not as precise. So that's how the ion ratio works. And then you see in the unknown sample is down here. The unknown, also the ion ratio is calculated, and then it is applied whether it is within 20% of the expected or not. You can see the swath, really, we need more data points, right? These peaks are much more sharply defined between the data points than the time of flight. So I would like to see a few more data points there, and that will also clean up at the lower concentrations the ion ratio. So is this important? Only if you need to do ion ratio to confirm your compound. I just wanted to show it to you because it is there, it is part of the software, and it is something that you would do with swath. So it's not something you can do with time of flight. But I think overall, the message is that the quantitation will be better with the time of flight because all of the data, all of the time is dedicated to the time of flight. we don't have any time wasted on the other MSMS experiments. Okay, let me save this, and then I will open for questions. So this is swath. SWATH. Anyone have any questions?
Mm,
No? Everything okay?
yes.
All right, let's take a look at where we are in the samples then. Maybe I just need to take a break for 5 minutes. Then we can look at the sample. Oh, we're still running the blank? I thought it would be a little faster than that. Okay, second blank is running, but must almost be finished. Yes, and then it will do the cal, and then it will do the sample. All right, shall we take a break until that's ready then, maybe?
Yeah.
So that's going to start at 3:27, and it runs for 15 minutes. So let's come back at 3:42. Is that okay? We'll take a break, 20 minutes break until 3:42, and then we'll look at that sample. And based on the data from that sample, we'll decide what we want to run overnight tonight, or if we want to make any other changes.
Okay.
Is that good?
Yes.
Yeah. Okay. All right. So let's take a break, and I'll see you
Yeah,
guys
I'm
at
at
3:42. Okay. See you. So you can always use the SCIEX now from the web page to make a help request to open a ticket. So anyone have anything else they want to ask or say or?
Thank you.
Sure, you're welcome. You're welcome. I think we had a good progress over the 6 days. It's not perfect yet, but definitely you'll get there. All right, guys. Well, then I wish you Merry Christmas and Happy New Year. And for sure, we'll speak again in January. Rami, I will just send you this report here perhaps later this afternoon, and
Sure.
maybe you can return it to me tomorrow or
No
early
problem.
next week or something, whenever
problem.
you have a chance to do that. That would be great.
Actually, I would like to thank you all from here, in the name of all my colleagues here at AUB. You've been amazing to us. It was a great support, and we look forward to working more with you as well after the new year.
Great.
Thanks a lot.
Absolutely, yes. You're welcome. It's my pleasure. We had fun together, so definitely we'll continue. Yeah, for sure. Absolutely. Thank you for that. Yes. All right, guys. So have a good afternoon and talk to you soon. Take care.
Take care. Same to you.
Okay.
Bye-bye.
Bye-bye. Bye. Data we had before lunch. Now I didn't prove it to you yet, so you probably are wondering why, because I guess the default would be that you would think that the MSMS is better. However, for pure quantitation, I think you will find that this TOF MS data is the best. So we'll keep this open and we'll process the swath. So let me ask you then, in terms of so you wanted to confirm against your standard what you expected. So we have the answer here of something approximately 62.4 nanograms per mil. Is that close to what you had expected?
I think it's close because it's on the end of the experiment. I don't know actually how much degradation happened. You know, I could.
Okay, I see. So
to compare this sample with a reference one to see if I have the same degradation products. The references are here and there. That's what I need to know.
Okay, so this is not quantitation then. You want to confirm the presence of other compounds in the sample.
For this one, yes.
I see. Okay, so that would be two separate experiments then. One would be the quantitation, which is what we are
Yes.
doing up to this point, and then the second one would be to confirm the presence of other compounds. So in order to get the most from the instrument, now you could do that in one experiment. You could. But it's not going to maximize the sensitivity for both because they are quite different experiments. So in this data, okay, these are the results we got. We didn't have anything to compare them to yet. But let's talk about the methods, right? So this, we have a TOF MS only method. So as you see, when we look at the method, all of the time in the method goes to the TOF MS. So we are maximizing the instrument time on the TOF MS. So that is why I think that the TOF MS only will be the best method if you just want to do quantitation.
Yes.
Now the other methods can be used for quantitation. It's not a problem, but you have to realize that, so if we open one of the IDA methods, you have to realize that the instrument is now doing many things. It is not just doing the TOF MS anymore.
Yes.
So your sensitivity will not go down by 5 times, right? Because we went from 500 milliseconds to 90, but it will go down, I think, because you have the IDA, which takes time. Now, what does the IDA give you? Well, the IDA could potentially identify through library search or through other means, structural elucidation, your other components in the sample. And swath the same. So I guess I didn't understand that this morning, that I thought this was straight quantitation. Okay, so you have some other things to analyze. So they are in this PDF
Yes.
document. Okay, so basically we need to know what they are, either a mass or a formula.
These are some degradation products at a max.
All right, so
Some with the mass and the
Right.
retention
okay.
with the connected one.
Okay, so exactly. So basically, you will modify your method to contain these. Now, you will not be able to do quantitation because you don't, well, as far as I know, you don't have standards of these compounds.
Yes, I don't have.
Right. So one thing I can show you is how to use a calibration for one compound on another, but without having real standards for these compounds, it will be difficult to do absolute quantitation. Now, you might be able to do relative quantitation, but you would need an internal standard to make it relative to. You would need something additional to this to calculate your own relative areas, and then you could say, for example, okay, it went down by 2 times, or it went down by 4 times, or something.
Yes, I just want to confirm that this that I have 1 or 2 of these byproducts in my sample. The presence of them is enough. I want to try it because on the HPLC here that we were using to try it, and the MS wasn't sensitive for our samples.
Right. Okay. So I think you've done that already, right? Because how did you get this retention time?
It's on a reference paper.
Ah, okay. All right. So that's not going to translate, right? Because they are using some completely different,
Mobile paper.
right, column and
Yes.
so on. Yeah. So don't expect that. Okay. So, okay. Well, the easiest thing to do is then to go back to analytics, and what we can do is we can take your processing method, so we can say results new, and we can take that unknown sample that you ran, So,
This one.
yeah, right here, right? This one. And let's grab one of the others too, just so we have a positive for the SMX. And then we can say we can use the same method what we have, SMX1. Oh, 1 second. Okay. And then we can edit. So we have the foundation of the method. We don't need to play around too much. But what we can do is we can add the other components here.
Yes.
And that's an easy copy paste from the Excel that you have. We don't need first one, right? So if that happens, sometimes I just go to Notepad, something not right with the format. Just paste it here and then select all again and copy it. Try it now. So maybe we cannot have some character. What character is not visible? Might be the brackets, I'm not sure. Oh. There we go. So why I can't see. So why? So let's take all of this, put it back, or maybe it's the next compound, huh? This doesn't work. Oh yes, and you see now our wonderful software, there is no extra space anymore. So I cannot. Oh. See the problem? There's no extra line appearing. You would think copy paste would be easy, right? Not quite. There we go. I have to force it to do something. Okay, paste there. So why? I don't understand why it gave an error when we tried to do all of them. I will try again. Back to Excel. Here's Excel. Just make a new page. All right, maybe this time we get it. Well, I don't know. Doesn't want to cooperate today. Which means it's going to take a long time. Can I take like this? Maybe this was the problem. Oh, I missed the O. Didn't work. Okay, let me try now the rest. That was the issue or not. These formulas are all okay. Yes. Copy. No, it still doesn't like it. I don't know. Never saw that before. I'm going to do this back. So this is N. All right, last one. Okay, so what we can try to do is to set your unknown as the reference, because that's the only chance they could be there, right? You don't have them in your 60 ppb for sure. And then we can go, finally, we can go to integration, and we can see if there are peaks. Doesn't look like it. Yeah. If they are there, they are below the detection limit of the instrument.
Alek, we always have to do it this way. There's no easy way to add the rows in the table.
Yeah, I'm as surprised as you. Normally, you can just copy paste. I don't know if it has something to do with all the weird characters. But normally from Excel,
but I mean, is there a way, like on this table, to add more rows underneath?
Yeah, I see that as a bug every now and then where the extra row doesn't appear. Sometimes it appears and it's easy, and sometimes not. So, yeah, unfortunately, you just have to go and you have to make it reset by doing something, by choosing another sample or closing or opening.
Okay.
Yeah, unfortunately. Yeah, if there was a faster way, I would obviously do that. Yeah, I don't know exactly what's going on there. But normally
Sorry, Alek. If you use the chemical formula only from the Excel sheet and you paste it, it won't work as well.
Should I can try that. So
not now. Now you just finished. Yeah. Maybe you can add for it. Maybe.
Yeah. Usually copy paste is easy. So I don't know.
Yeah.
It could be
maybe from Excel sheet.
It should be from the Excel sheet. Fine. Maybe because this Excel sheet, maybe because they are small cases. That's why, or maybe for this reason, enable editing is blocking it. I don't know, but that's also why I went to Notepad. So I went to Notepad and then I fixed this 1O here, and then I copy back. So this should be without any strange format. That's but so how does it know that? So something is. It's keeping the format. That's the problem. That's the problem. Usually Notepad is removing the format. That is a little bit strange, unless something is wrong here and I'm not actually copying. See, that's why. There we go. So I was using the keyboard and I was not using the. So now probably it works. Nope. Honestly, I don't know. the data are in an invalid format, check the source of the text. Usually I do it from Excel and everything is fine. So I'm not sure what exactly is going on there. This to me is fine. Maybe this weird characters are somehow, but when you do it one by one, it works. I don't know. We can also try just the, so this is what my suggestion was. So here we go.
Perfect.
Yeah. And then maybe we can even grab this. Here we go. So today it accepts the columns, but still we don't have that. We don't have the line to continue. But now we have errors because it doesn't accept duplicates. So you have to at least have a different name.
Yeah.
Okay. There it's come.
Thank you.
Yes, you're welcome. All right, so on to more interesting things than copy-paste. I'm sorry about that. So it looks like, so we can do the real processing and see, but as this is the unknown sample, it looks like we don't see a trace of these present. So maybe they are below the detection limit, or they are maybe metabolites that are not around, degradation that don't hang around. Do they say anything about which ones are stable or not?
No, I don't. I only the intermediate is not stable. The one they have to.
Yeah, because here they are showing an MH plus for each one, right?
Yeah. Can you check for the sample? If my sample has on the M-axis has something different than this, other than the peak for SMX?
Right, so we can run the unknown analysis on it, like we did yesterday with Tony's samples and Bassam's samples, or not yesterday, sorry, last week. So we can do that and we can see what peaks come up. There will be definitely peaks. And we can also compare it to the blank and see. So that's something, actually, we did that already on those samples. So you saw the workflow for that. We can even use the same unknown method. But I'm a little bit surprised why. I mean, I don't know the work exactly, right? So it's hard to say. So 209 is one of these masses, 209. At least we are correct. Yeah, okay. So, yeah, and they are all MH plus. Yeah. All right, well, what I will do is I will save this because you don't want to have to do that copy paste again. So this will be the SMX. These are degradation products, you said? Degradation products. I guess there's not really any need to process, but I'll just process. So we can use the IDA to see if there's any differences. And what you could use is you can use the injection of like the 60 ppb SMX only as a blank, as a control, and then you won't find anything that's at least coming from the chromatography. So we can go to settings and we can say one at least. So the 60 ppb worked. And so approximately what concentration did you use in your sample? Because just by coincidence, it looks like that your unknown sample has about the same area as the 60. Oh, we know that already because we did the quantitation. It has 62. Yeah. Yeah, sorry, I'm forgetting that. Do you know approximately the concentration you added?
Yes, at the place of the experiment, I added 100 to 50, 600, then a degradation happened. So 60 is quite good because
So
there is a
40% is gone somewhere.
Yeah.
And you accounted, of course, for any change in volume or anything. Yes, okay, great, yeah. All right, so yeah, I think we can safely say at least not a substantial amount of those products are present. So let's try the unknown. We can go to results and new. And basically what I'll do is we can use now the IDA. So at least we have the MSMS if we do find something. So that would be, oh, here you have an A and a B.
A was without triazine, B was triazine.
Ah, okay, all right. So let's forget the triazines for now. And we'll throw in a 60 BBB as a standard and also as a blank. And then we will use the same unknown method that we used yesterday. So non-target screen with the control. Okay. And we select the control as the 60 ppb. So basically it will find anything in the sample that is 5 times bigger than the control, and the control should only be solvent and SMX, right? I remember correctly here, we had that slider bar a little bit wrong, right? We were getting too many peaks, so I'm going to put it here. Let's take a look also at the retention times. Because okay, I will save, but I will need to check. Because, yeah, your retention time is
0.87, I think.
Yeah, very early. So let's adjust that so that, and see here, put 0.7. And you have sulfur in your compound, so we have up to 5 sulfurs. Okay. CHNOS, right, is the main products, nothing else, right? CHNO&S, no, nothing else weird. Okay. So basically, I think then I'll remove the P and the C because it'll give us a lot of hits. Okay, so we'll save that, and we'll see what we do, how we do. All right, so here are the results. And what we need to do is to go to samples and to make sure that we are looking at the sample and not the control. I often make that mistake, forget that point. So make sure you're looking at the sample. And then what we can do is we can say recent table settings, and we have a non-target, yes. So that's good. And then we can see here the results. Now let's clean this up a little bit so that we have all 3, yes. And then here, just make 1 row. Otherwise, it's going to be a little bit messy. Okay, so in the chart, we can now sort by area ratio. Okay. So yeah, that's a thing. So these are just poor integrations. Well, we don't see too much. We can also, so that's just a problem of lack of integration. Let's see by area. The same. So these are all where it didn't integrate in one versus the other. That is in the sample, so that's one of the triazines, right? 6. So that's not coming in our table because it's bigger in the control, but it means that that the instrument is working. That's good. So, well, I'm a little worried about the fact that you have the sample in such high methanol. Where are those chromatic pictures again? So this is SMX, right? And SMX itself is coming very early in our runs. Now,
this, for example, I can't see this and here when I run my samples because it's very early here, 2.02. I have some access on 0.87, so I can't see any amount under that.
Yes, but I'm worried why we are getting such an early retention time. We should not get an early retention time. This column is a column, it's a polar column. It's designed to give retention time of polar components. And I would say this is not even that polar.
Yeah.
So I would like to ask you to prepare a standard of SMX again, but in maximum 10% methanol, or even remove the methanol altogether. Yes. And to prepare it in as much water as you can. And is there anything else in your samples? Do you have any buffer?
Oh, I have in my sample, I have only the ionized water with percentage and SMX. The solvent that I use in the HPLC is 60% methanol, 60% the mobile phase. The mobile phase that I use is 50% methanol, 50% DI with formic acid. My sample only contains SMX with percentage and 40 ionized water.
And how much per sulfate?
2 millimolar.
2 millimolar.
Yeah.
Okay, that's nothing. And formic acid is 0.1% or something like that?
Yes, the mobile phase.
Okay, so I think it's the methanol. That's got to be the key, because we are not running the same chromatography, but why they got 8 minutes and we got less than 1 minute, and we are running a good gradient. So something is really not right in what we did. So the only thing I can think of, just chatting with you, you tell me all the conditions, is that 50% methanol is too high. Do you have time now just to run and to prepare one? And just one concentration. It can be 100 ppb or 50 or something, just in 100% water? Or you need more time to do that?
I can.
How long do you think it'll take you?
Maybe 5 minutes and I'll be back.
Yeah, perfect. Yeah, that's great. Then we can start that running, and then we'll talk about the swath while it's running. And then that way, after the swath is done, we can have a look and see if this is the problem. And then if this is the problem, you can prepare your samples again, and we can run tonight and check tomorrow.
Okay.
That's a good plan, yes?
Yes.
Okay, great. All right, so if you go and prepare that, then we'll wait for you. Great.
Yeah.
So it's soluble in water, so it's going to be fine. So they don't tell us the column, huh? Text S2, where can we find that? Maybe at the end? Oh. Hmm. Would any of you have access somehow to get that? Maybe that's a supplemental material. While she's preparing the sample, it would be nice that we can look at that supplemental material and find out exactly what conditions they are using. Table S1, S4. Yeah, we need the supplemental information. Huh? Maybe there's a link on the main page. Document is current, more information. So here we go. I found it. Supplementary information. All right, so here's the abstract, here's the supplement information. Okay, that wasn't so hard. Easier than copy-paste, huh? All right, so here we go. Details of the HPLC system, number 6. All right, so what's here? Oh, this is chemicals. We need S2, right? Yeah, here we go. All right, so they even use the same HPLC what you guys have, and they use a regular reverse phase column. You guys see that? That's a normal C18 column. So we have a polar column. We should have even more retention. So I really feel that the injection solvent is what is the issue. Everybody understands that, right? And even this is a kinetics column. They did use pretty low percentage, so we could change that. The maximum they go to is 35% organic. Do you see that? So we could also adjust our gradient a little bit, but we have a polar column. Excuse me. So nothing else interesting in supplemental information. No chromatograms, huh? Ah, here we go. So these will be useful for us in interpretation of the MSMS. What is the difference between their column and ours? Somebody asks. So their column is, I would say, more garden variety regular C18, and our column is designed to retain better polar components. So in a reverse phase chromatography, the packing material is non-polar. So reverse phase chromatography is very good at retaining non-polar components. like attracts like, right? So the problem is with polar components. So I recommended this polar column because most biological components are, let's say, polar, and so it will do a better job of retaining polar components. So that's why I'm surprised that we have retention time 0.8 minutes and they have 8 minutes. So they really got a very good retention of this component. Oh, and here's something interesting. This must be exact mass information. Yeah. So this is the retention times, fragments, and accurate mass. Yes, you're welcome. So this is also interesting. Fragments and masses. Great. This should be in the paper, in my opinion. They put this in the supplemental information. It's like hiding it. All right, so let's just check again. I think, yeah, so hypersil BDS C18, I believe that is a thermal column. Look, yeah. So robust general purpose column to use in a wide variety of applications, you should choose this column. Economical, exceptional reliability. It doesn't, so our column should have more retention of this component than this column. This is a wide, a very, very generic column. I'm surprised by that. Let's have a look at our gradient. Well, it's not really fair. We asked her to go and do something and then we start changing the method while she's gone, right? That's not really fair. So we'll wait for her to come back. But I think we'll play around with the gradient a little bit and we'll show her this supplemental information too. All right.
شو بدها تعمل زهراء؟ شو بدها تحضر سامبل جديد؟
سامبل 1 سامبل.
بس ما هي سامبل محضرتهم مثلا محضرتهم مثلا
product. I noticed a difference in the Excel sheet.
طلعت I think على
Okay, let's take a look at that.
طلع انا بالاوفيس فين واتساب
قريت هلا لك عن مركز الايميل.
اجي لعندك شو قايل لها ألك
عشان نعمل مشي
ناظرها لتجيب السامبل هي قالت له 10 دقايق تحضر وتجي
بيكمل الشغل يحكي بشغل
ما عم شو عم بيقرا هو هيدا
عم بيقرا
هذا عم شو بده يعدل المثل.
So Excel sheet, here we go. So Excel sheet, this one, huh? C4H8ON2. Okay, and then maybe that should be in negative mode. Take a look. Paper. There we go. That's what I want to see. All right, so come on. All right, so where's the 99? 99 is MH plus right there, lower left, right? Also at the top, it's the same. So you said we got 101. Did they make a mistake? So analytics. Right here, huh? No, this is the unknown stuff. And I should apply the other settings, huh? Actually, the quantitation settings are not so good for this. We want to do target settings. Then we have the formulas. There we go. So C4, it's like a mistake. C4, H8, O, and 2. We have 101. Okay, so we just do a quick manual check. Carbon is 12 times 4, hydrogen is 8, oxygen is 16, and nitrogen is 14 times 2, right? 12 times 4 is 48, and 14 times 2 is 28. So we have 28 plus 48 plus 8 plus 16 is 100. I don't know how they got 99. That's wrong. The paper's wrong. I guess they meant that, no, that's completely wrong. MH plus. Let's see if maybe they made a mistake in the formula. So let me blow this up. There we go. All right, now it's big. Okay, so we have here 2 nitrogens, yes. We have 1 oxygen, yes. How many carbons do we have? There's 1 here, and 1, 2, 3, 4 carbons is correct. Now we should have 8 hydrogens. Here's 2. 1, 2. There's none there. There's 1 there and 1 there. So that means 4, and then 5, 6, 7. So they have 7 hydrogens. So maybe they made a mistake there. Am I a little bit dumb, or what did I do? Did I do something wrong? Okay, so how many hydrogens in this compound? So that has 4 things, so there's no hydrogen there. Here there will be...
I believe there are 6 hydrogen.
Yeah, there are 6 hydrogens, right? Here there's 1. I'm stupid, right? That I said 2. 1 is there, none is there. So you have 1, 2, 3, 4, 5, 6. So it should be H6. Right? Everyone agree with me? C4, H6, N2O. So here, this should be a 6. And then it's 99. Because then we have 48 plus 6 plus 16 plus 28 is 98, plus 1 is 99. Good catch, whoever that was. That's the kind of detail, attention to detail we need here. So where can we change it? Okay, we have a lot of things to tell her when she comes back. We have to remember them all. So here, this becomes a 6, right? And now we have 99. Okay. So now let's do the integration. Still, we don't have. I bet the stuff doesn't, I bet most of this is more polar and it doesn't retain. Shows you how important chromatography is. We use the same gradient as Tony's samples, right? So let's go and look at his samples And I want to see, maybe from the UV data, we can see what is the flow through. What I mean is, what is the non-retained fraction? So his samples were like this ZK stuff, right? Okay, let's have a look here. And we can say show XWC and say okay. So yeah, so this is the, so that, this peak here of stuff, it's usually much more obvious in the UV chromatogram than in the TIC. This peak of stuff is what we call the non-retained fraction, or we sometimes say the flow through, or some people say void volume. Those all mean the same thing. And what that is the stuff that goes through the column without being retained. Now, the column has some length and so on, so it takes some time to reach the detector after the injection. But that time is if it just went on a straight path without any stopping. So anything that is at that time would be considered as non-retained. And if you look into, I should remember some names here. Her name is Sarah, right? Correct? So if you look into Sarah's stuff.
Zahra.
Hello.
Hello.
I'm back.
You're back. Okay, great. We did so much while you were gone. Actually, we have to explain it all to you now. Which, don't worry, we'll do that.
I have something to say.
Okay.
I already prepare my samples with 100% deionized water. It's the same sample as the one that I already ran them. Do I could change in the gradient illusion for example, not 50% methanol, not 50% deionized water with chromic acid? I think the problem is not in my sample because my sample doesn't contain methanol. The illusion process using 50% methanol and 50% deionized water, I think this is the problem because I just trying in the beginning and very low retention time. I think it will modify.
Absolutely, yeah. Actually, we came to the same conclusion because we were discussing ourselves about what could be the problem while you were gone, and we came to the same conclusion. And but just to be clear, here we are not using 50-50. We are starting at organic. Well, actually, let's look. I don't remember.
To see the IRC method that I prepared.
Yeah.
It's ZABK. Yes.
You changed the method. Okay, let's take a look. I didn't know you used a different method. Okay. Let's have a look together and see. Wow. Okay, yeah. Right. Okay, yeah, we can't use, okay, this is isocratic. We don't want to use isocratic methods here. We have a nice gradient system. Pretty much you should always use a gradient analysis. So yes, okay, it makes sense. I thought you were using the same gradient as Tony. Okay. Yeah, all right. No problem. Okay, let's discuss what we did while you were gone. So first thing we did is we found the supplemental information.
Yes, I have that.
And where did it go? Here it is. So we looked at the supplemental information, and we looked at these columns that they are using, and we had a discussion about these columns. And this is just a standard C18 column, what they used. So what that means is actually you have a better column in terms of polar components, because the column that is on the system now is a Luna Omega polar C18 column. And that column is designed to retain polar components better than a regular C18. So we should have better retention. And actually here, when we look, they also did isocratic, but they did isocratic with 30% organic and 70% water. So that means they would have more retention than you. Okay, let's forget about isocratic. It's much better to run a gradient. You have better control, and you have a cycle that repeats every injection. So I would say convert to gradient. And actually, if you look into the next method, the MS method, you see that they do run a gradient,
Yes.
but they don't run a gradient that's very strong. So that's also interesting. It looks like they go to maximum 35%. Yeah, there's no number bigger than 35, right? So the maximum they go is 35% organic. All right, so I think the injection solvent will be important, but like you said, I didn't know that you changed the gradient. Okay, so no problem. It's now we understand. So basically, I think what we'll do, we know that Tony's gradient is working nicely, or the gradient we use for Tony's sample. So let's open that one.
I think this one.
This one? Did we have problems with pressure? We used 0.5 or we used 0.4? I can't remember. Why did we go to 0.4? Oh, I remember. Because we said we wanted your peaks to be a little bit wider, right?
Yeah. To have more data points.
More data points, exactly. I remember now. Sorry, it's hard for me because every day is a different customer with a totally different setup. Okay, so here we have gradient. So what we'll do is we'll take the same gradient and we can, well, actually, I think we should just run the same gradient for now and work out where these components show up. So, like I mentioned on the first day, I think, when we made the methods, if you start with a 6-point gradient like this one, and by 6 points I mean 1, 2, 3, 4, 5, 6. If you start with a 6-point gradient, then I'm almost 100% sure it will always work fine. And then after you do your first run, then you make a modification based on that. Especially when you guys are starting out, I highly recommend you to do that. It'll work. I'm almost guarantee you it'll work great the first time. And then we'll see, if the compounds come very early here and there's nothing, which is kind of what I expect based upon reading that supplemental information, then we'll cut the gradient and we'll shorten the time, or we'll make it more shallow, or so on. But we'll just start with this to see how we do. Okay, so this is fine. We'll use the 400 microliter one at 15 minutes. Okay. So did you put your samples in the auto sampler? Already in the auto sampler. Okay, great. So let's open the batch, and I guess this is your batch, right? Okay. And so what we can do is we'll just add to the bottom. Okay, whoa, sorry. Slow response. Okay, now we'll need to run a blank. So basically, we'll copy that twice. And then, so what have you prepared for us? What concentration?
100 ppb.
100 ppb. And is it just SMX? Only SMX?
Yes, the DI9 is good. Yes.
In DiH2O, right? Okay. So then we will use so we'll use okay, the TOF MS will be fine. Oh, well, let's do the IDA. So we have MSMS. Do we want to do IDA? Yeah, let's do the IDA. So we can use this one, right? That's a 15-minute IDA, and your targets are in that range. Yes, and then, but then we'll go here. We'll use the 15-minute gradient at 400, right? Okay, and blank is in position 46.
Yes. I want to put on the high value. No. And the standard that I prepared, I just put the flat only the blank.
Oh, a new blank? Okay, great. Just tell us what position you put it.
The blank is on 46.
36, okay.
I put the standard on 47.
57. Okay. So just to confirm with you, because your voice is very small, 36 for the blank and 47 for the sample.
No, 46 the blank.
46, okay. All right. We'll run 2 blanks because we're just coming from a cold system.
Yes.
And we'll change this to be 43. 44. And this will be 45. And this is not TOF MS. This is IDA. And what, oh man, yeah, I forgot about that. Don't use the delete button. You delete everything. ZABK 045. And then we have TOF MS IDA. This is why we don't type. Okay, and then we have 100 BPB SMX in DI H2O. All right, great. Okay. All right, so we're gonna submit those 3, right? Okay. Let me equilibrate for a second. So the MS method doesn't really matter. Choose that one. And the LC method is the 400 microliters, 15 minutes grad. So just double check because I went very fast. So we have 2 blanks and then we have the sample in DI water. We're doing IDA, MSMS in this mass range, 70 milliseconds, fine for the MSMS, and we have 15-minute run. Okay, and that matches the Luna Omega at 500 microliters with a 5 microliter injection at a 15 minutes gradient, okay, at 46 and 59, and our data files are all unique. Oh. Okay. So we'll save that, and then we will submit those 3 samples. How does the pressure look at 400 microliters per minute? So you've got 240 bar. Okay, that's pretty good, but the oven is probably not hot yet. Yeah, the oven is still warming up. Okay. That'll come down once the oven warms up. All right, so while it's equilibrating, now we have to remember all the things we did while you were gone. So, okay, we did the supplement, we found the supplemental information and we looked at the gradient. So I think that's important. And we talked about the column. One of your colleagues found a mistake. This is mass 99, but the formula in the Excel sheet had 8 hydrogens. So this actually should be a 6. So we were looking for mass 101, but actually it should be mass 99. If you look at the structure, there's 2 hydrogens here. There's 1 hydrogen here. And then here there's 3. So 6 hydrogens total.
Yes.
Not 8. I think it's their mistake in the paper. So we fixed that in the processing method. And now pressure is going high. And now, oh, maybe I can't reach that. Oh, I can say okay. And so we fixed that in the processing method. And now, so that used to say 101. Now we look for 99. We still didn't find anything, and there's no peak, but at least we have the right mass. That might be a little something there that also went straight through. Yeah, look, mass error is correct. So probably some 99 is there, just went straight through the column. Maybe. Could be that it's all there, just didn't retain at all.
Yes.
Yeah. So in some ways, you have to pay even more attention to chromatography on this system than another kind of mass spectrometer. In order to get a good peak shape for the unknown to work. That's important. Okay, did we do anything else while she was gone? I think that was it, right? I think so. All right, so why don't we continue in the processing, and we'll talk about swath, and we'll talk about time of flight. We'll talk about TOF MS versus swath quantitation. And we are planning to do the swath while the samples are running. Exactly, yeah, right. We'll start that now. Just let me check the pressure one more time, because I noticed it's going a little bit high. Yeah, now it came back down. Okay, that's reasonable. And the temperature is almost there. It'll go down a bit more as the temperature penetrates the column, because this is the temperature in the oven, right? Not actually in the column. And that's also why I like to run 2 blanks when the system is coming from cold, because the first blank is just like a get ready kind of thing, you know. And then the second blank is my real blank if I need it for processing to be a 0 or something. And then the sample will start from the 3rd injection. All right, so I will submit the samples. So we just go, we have auto calibrate. All right, I'll do it every 2 samples now. I'll cheat a little bit so we get a calibration just before our sample instead of every hour. I'll put 2, and now we'll submit those 3. Submit 3 samples of the 45. Okay. So let's take a look at the queue. Here's the queue. Here's our runs. So the cal is going on right now. then we'll do 2 blanks, and then we'll do another cal, and then we'll have our sample. Okay, so start. That'll be ready in about an hour. Okay. All right, so we're going to talk about swath, right? Okay, so now let's go back to the lecture slides briefly. Oh yeah, it got closed probably because we did a reset, right? So here we go. All right, so what we can do in swath, which we can't do in IDA, is we can use the daughter ion for quantitation. So where's the swath? Yeah. So this was another slide about how swath is working. So just to remind us before we go and look at the data, here you have a chart that shows you what the method is doing. So we have retention time here on the x-axis, and on the y-axis is the m per z of the parent. So what you need for quantitation is you need to do the same thing every cycle. So one cycle here is shown to you with a green arrow, right? So we look at a parent that's in the red window. It's measured in this cycle and this cycle and this cycle. It's measured in every cycle because swath is doing the same thing every cycle. In other words, what am I trying to say? Swath is not picking and choosing parents to do MSMS on like the IDA, right? So we can't use the IDA MSMS for quantitation because it's different every cycle. It chooses some, and then it forgets them, and then it chooses others, and things are going above the threshold and below the threshold. So it's very complex what's happening. So we can't use the MSMS in IDA for quantitation, but in swath we can. So why would we want to do that? What does MSMS give you? So MSMS gives you another level of selectivity, right? So when we did the quantitation, we just did it. We looked only at the TOF-MS scan. Now, on this instrument, we get quite a lot of selectivity through high resolution. And as you could see in the quantitation that we did, we had very clean chromatograms, right? Let's go back to that. Here, I think it was, right? And yeah, I'll just show my 12 little chromatograms again, right? So here's our 12 chromatograms, right? Even at low concentration, these are small chromatograms. Did it update or did did it freeze? Oh, it's probably doing some calibration in the background. Okay, so I have to remember to go a bit slow. Okay, so if you look, right, this is coming just from that XIC width, 0.02 wide, focused on the parent mass of the SMX. And we have really nice, clean chromatograms. This gives us this sensitivity here. Now we'll go in swath and we'll do the same thing. We'll look at the same chromatogram from the swath data because we have the TOF-MS scan in the swath data as well, but we additionally have the MSMS data. And we can use the MSMS data to make an XIC that follows a parent and a daughter. And that will give us even more selectivity. Now, we don't need it here because the TOF-MS chromatograms are okay. But in a very complex sample, a very dirty sample with many, many things in it, like a plant extract or a bacterial extract or something, you may have interference, which you do need another level of selectivity in order to focus on your compound. And then that's when you can use swath. So I think overall, 99% of the time you will use the TOF MS for the quantitation because it works great, as we see here for the SMX. But the swath may help us. So what do we need to know? Don't forget, whenever we do swath, we have to know, right? We cannot expect to find out from the swath. So from the data, we need to know the daughter ions, right? We know the parent. The parent is SMX, and we know the formula. What's the formula for SMX? We can find that from our screening here. This is SMX. Here's the formula: C10H11N3O3S. So that's the parent. Now we need the daughter. So what do we need? We need an MSMS, right? So the first thing that we're going to have to do before we start to process the swath data is we're going to have a quick look at the IDA. Why am I going to look at the IDA? Because the IDA is clean MSMS. So somewhere in the IDA data set, we will have selected the SMX, and we will have done clean MSMS on it, and we'll have a clean spectrum. So we'll know all of those daughters came from SMX. And we can get the exact mass of the daughter. And we might choose several daughters to see which one is best. And at the same time, if you were interested in building a library, you could add that spectrum to the library as well. Okay, so let's go and do that. First step is process the IDA data of the SMX. So let's find it from yesterday. So here it is, TOF IDA, right? So let's take the 60 ppb. That was quite a nice, strong concentration. And I can use the same method what I have for SMX, right? So what I do with the method, whether I do screening or whether I do quantitation, is really dependent on what I do in the chart, not so much what I do in the processing method. And I can say process, and I get a new chart now with the MSMS data. Oh, minimized. All right, so here it is, and I could say my table settings for screening, targeted screening with library search. Now I can look at the data with the peak review. And now I see only the MS. Why is that? Because previously I was looking at quantitation and it was set here to XIC only. So under view, now I want to see also the MSMS. So this is the XIC at 60 ppb, collected under the IDA conditions. This is the parent, and these are the daughter ions. So I know these daughter ions came from this parent because this is IDA data, it's clean. We selected this parent for MSMS. So it just takes a little bit of legwork. I'm just going to write down some daughter ions. So 156.0118, 108.0449, and one more, 92.0497. Now, if you did want to add this to the library, it's really simple. Right-click and add spectrum to the library. We actually didn't talk too much about building your own library yet. Do you have Library View installed? I guess you do. If not, yeah, right. So you have Library View installed. And, oh, we did this, right? We did Library View together. I remember because we checked the license, right?
Yes, we did.
Yeah. So, while we're here, we'll just talk a little bit more about the library, because it's a good time to do it from the IDA data. And I think it's good practice, every time you run a compound in IDA on your way to doing swath, you have the IDA spectrum, why not add it to the library? Oh yeah, you guys have a lot of libraries. Okay, great. So maybe you even have this compound in the library already. Sulfameth something, right? Yeah. Is it this one? Sulfamethoxazole? 10, 11, yeah. So it's even here in the library already. So that's nice. And you have MSMS spectra. So we can also now confirm that we have the right daughter ions. So I wrote them down on my paper here. So I'm just looking at my notes. So we have a 156, check. We have a 108, check. And we have a 92, check. So we did a good job there. So our data matches the library. That's always good to confirm. So in this case, we don't need to add to the library, but I'll just show you how to do that. Oops. So you just right click and you say add to library. And now you have this library addition window, little wizard. You can change the name if you want. So I guess it would be better to write the full name, right? Sulfamethoxazole or something, whatever. Okay, and then library. Now here, I highly recommend that you do not add your own compounds to these libraries, because these libraries are protected by a license. And if you remember, I think that's what we did last week. We had to activate the license or something. So if you add your compound to one of those libraries, it will become protected by the same license, and then you will not be able to move it or transfer it or anything at the future. So I strongly suggest you to create your own library and to add your compounds to your library, and then they're yours and they're available. So how do you do that? Go to the library view, and you have here plus. You can make your own library. Add a new library. And you can just say whatever you want. For example, custom sulfa antibiotics, right? And you can say add. And are you sure you want to create? Yes. And now you see you created it. Where is it? Right here. And now this library is yours. It's not protected by one of our SCIEX licenses. So you can move this to another computer, or anytime in the future you can play with it or do whatever you want. So I highly recommend you to do that. And then in SCIEX OS, when you say add to library, now you can find it here, custom sulfa antibiotics. Yeah. So you can do this procedure. I won't add this one because it's already there. You can do this procedure, and then you start building your own libraries, which are separate from the SCIEX ones. So that's really easy how to add the library. Okay, so now we did what we came to do, which is to find a few daughter ions which make sense for this compound in order to process under swath. So now we'll go and we'll make our swath quantitation method. So we'll go to results and we'll say new, and now we're going to use the data that you ran under swath. Sorry, I just had to drink some water. Come on. Alrighty, so let's have a look here. All right, so here's the data, right? You've got a 1 ppb, a 2, a 2.5, all the way up to your sample. Okay, let's add both of your samples. Okay. So now I'm not going to create a brand new method. what I will do is I will start with the SMX method, and I will edit it. And then that way, at least, I don't have to write that formula again. So we'll choose a reference sample. We've been working the whole time with the 60 ppb, so we'll just continue with the 60 ppb. And then we have components. Update retention times, doesn't really matter, the sample is the same. Okay, so now here is our components list. And as you see, we have SMX here with the formula and the mass, XIC width, and it's from experiment number 1. So now what I'm going to do, I'm going to keep that there, and that's going to look into experiment number 1. And now I will add SMX, and I will say daughter 156. So it's going to be the same formula, C10, H11, N3O3S, the same parent, but I'm going to put the exact mass of the fragment, 156.0118. And as I do that, see what happens? It changes the experiment index. It knows. And it knows that that should go now into the 9th experiment. Why does it know the 9th experiment? Because the 254 fits into the 9th window of our swath method. That must be, I would guess, that's from 250 to 300. And then we probably did 10 was 300 to 400 or something like that. I can't remember exactly what we did. But so now we're getting not an XIC of the parent, we're getting an XIC of the daughter, which is coming from that window, the 9th window. So let's just go back to the training presentation, that one slide we were looking at, right? So we have 10 windows, and it's taking the 9th, and it's following the daughter of the parent, which every cycle is now in that 9th window or 9th swath. That makes sense to everybody? Yeah. So I'm just going to keep going and put the other daughters in. So D108, and it's the same parent, right? So C10, H11, N3O3S, same parent. And now this fragment is 108.0449. Come from the same experiment, because don't forget the experiment is based on where the parent is. In the training presentation, right, this is not mass of the daughter, this is the mass of the parent. And then we'll do one more. So we'll say SMX, daughter of 92, right? C10, H11, N3O3S, right? And then here we have fragment mass 92.0497. Now we set up our quantitation method for the swath data. Now we're going to talk today also about ion ratio. I think I mentioned that this morning that we skip it. So in order to do that, I'm going to put here the same group. So now I put all of these ions, all of these XICs into the same group. And by doing that, the software will know that the ions are coming from the same compound. And we will be able to do something called ion ratio, which will allow us to add an extra, let's say an extra confirmation that we are following the right component. Hang on a second, I think there's a... okay. Okay, so from this point on, now everything is the same. Now we just have XICs that we need to integrate and so on. So we go to the integration and should have the same retention time, yes? We should have the same retention time. And we have all of our normal settings like we talked about. So if you have any questions, go ahead and ask, but I'm not going to go through the settings again. one thing that you can see is that the new XICs have the default settings. So I will just go to my original SMX and I will say apply to all these two little boxes, and I'll say apply, and now they'll all be the same. These are all XICs of the same compound, right? So one compound, one retention time. So we all have the same retention time, and the integration looks good. Okay. All right, so that's good. And then everything else, we're going to leave it exactly the same. We're not going to touch anything else about our method. The rest of the quantitation stuff just applies to how we will basically look at our data. It's not related to whether it's SWOF or TOF or nothing, or something. The only thing that's different now is we added these extra XICs, which are actually coming out of the SWOF data. Is part okay for everyone? Yeah. All right. So I'll say save as now. Okay. And I'll call it SMX, and we'll say SWOF. Maybe 001 is not so smart. SMX SWOF 1, right? And then we'll say process.
مش انت بقى معاك شيء وقت معايا أنا بوزيشن منيح امتى شو هذا أي نهار بيكون الأربعاء الجاي next Wednesday شو البوزيشن طيب internship نشوفها نعم ده كان شفتي ده بس هذا government office دي معاه
Maybe just a little slower because the instrument is running at the same time.
SCIEX هو Lebanese Center for Energy Conservation ماشي كتير مهم
Okay.
ولا بعدين internship يعني
All right. So here is our data. We see here all the samples, and don't forget now each sample has 4 traces, right? 4 XICs. So we see a lot more lines in our data sets than we did when we look at when we're looking at just the TOF data. Okay, so what I'm going to do is to again always start with my table settings, and I'll start with the quan because that's almost there. And you saw I put quan TOF, right? So now, what do I want to add? Actual concentration is there. So what I will add is the ion ratio stuff. And then we'll talk about ion ratio. So I'll put expected ion ratio. So ion ratio confidence. We'll have to go back and change that in the processing method because we didn't set that up. I forgot. Okay. At least we'll have those. So we have ion ratio, expected ion ratio, and the ion ratio confidence is a flag. So we'll put that with all of our other flags over here. All right, so that's pretty good. So what I'll do is I'll save those settings for you. Table display settings, export, and now you have pretty much a whole set of some nice settings you can use. So this is quan, and I'll say
ركب مهم
Swap.
الرجل بترك شغله أنا أنت تكمل
ion ratio.
شايف ركب مهم كتير شايف أنا.
Okay, so what's the first thing we have to do in any processing of quantitation data is sample type, right? So now this data is a little bit more complex because we have 4 excises per sample per analyte. So the easiest way then is to go to samples and just to look at one sample. And now I can change only 4 things instead of changing. Oh, I'm sorry. What am I talking about? Sorry, guys. Not sample. Look at one analyte. Now I have one line for each sample. Now I can change and changes for the whole sample. So the other ones are changing because one injection has to be one type. I don't have to do it manually and search through it all. Standard. So you see, as I'm doing this, I'm getting a lot of errors because why? If I go to look at my calibration curve, oh, I don't have a calibration curve because I didn't put the actual concentration. This is 1, and this is 2, and this is 2.5, this is 5, and this is 10, and this is 20. So by looking at the flags, how do you compare this data to the TOF data? It's quite a bit worse, right? Worse. So don't forget the SMX is the TOF data, but because the swap is taking extra time, we lose some quality data there. Yeah, so that's not as good. If we look at the peaks, we'll see that, I think. So there's our 12 chromatograms. I will use the truck tire to move the calibration pane up. Go. Then I'll drag this up, and I will drag this over. There we go. All right, so now I can see. Okay, so the interesting thing is the 1 ppb is totally gone. So if you remember, we did see a peak for that last time, but it was very small. So now there's not even any data points or anything. It's gone. The 2 ppb is here. The mass error is not very good. Actually, both of those have bad mass error, probably because the peak is so small, not because there is really any issue. We'll go and we'll look at the MS data. So keep in mind, what is that? That's just about 1400 for 2 ppb. Here's the TOF only quantitation. Here's the 2 ppb. Look, we're more than 2000. And we have plenty of data points. So that's the trade-off, right? We had, on this data that we're looking at now, it's the TOF only data. We had all of our time for the TOF MS scan. We didn't waste any time doing MSMS. Now with the swath, the TOF MS only makes up 10% of the data, right? Because there are 10 swath windows it has to do before it comes back to the TOF MS. So that's where all of our sensitivity and all of our data points disappeared to. Now, the quantitation is still decent. The accuracy is not too bad. It's not great because of data points. Right? If we had better data points, these numbers would be better. But the sensitivity is definitely lower. And we see that reflected also. The mass error calculations are not as good, probably from interference. Shall we go and look at that first? So I can come here and I can look at the XIC, the MS, and the MSMS. Now you see, that's what it's trying to do. Right? That's the peak right there. Oof.
بس 4 ونص.
It's not so big. Is it easier if I just put one row? Right, there you go. So that's the peak it's looking at. Right? So it's very hard to get an accurate mass number on just that. Okay. But we still have a peak area, we still have a little tiny XIC, and it fits on the calibration curve. Accuracy is not too bad. So it can be done, but it's not as good. So that's why I advise you to, if you really want the most sensitive quantitation, to do the TOF MS only. Does that comparison make sense to everybody? Okay, so what's the benefit of doing the swath, right? What's the benefit? Well, we have these other traces. So the other traces, let's go back to our view of XIC, and we'll go back to 12. So if you had interference in this TOF MS, and that may happen sometime, if you had interference, then these traces, these different MSMS traces, could add more selectivity. We have a problem with integration here. Oh, these peaks are below the limit. So for this, it's too small now. So maybe I will put this back to 150. Apply. Yeah. And here also, I'll do the same thing, just quickly. So, and you see our calibration curve is not complete. So, oh, we still have a few minutes. Yeah, what's up with that time? That time's really wrong, huh? Yeah, I was thinking there's only 2 minutes left, not 8 minutes. All right, done. Still running. Did we make some mistake in the method we chose? 15 minutes. 15 minutes. Clearly not 15 minutes though, huh? Let's have a look and see. What did we do wrong? All right, so what method is this? Oops, Q. TOF MS IDA, 90 milliseconds, 15 minutes. Done. Off MS, this one, right? So that is 15 minutes, that's fine. Must be the LC is not 15 minutes. Ah, which one is it? It is 5 microliter injection, 15 minutes gradient. 5 microliters, 15 minutes gradient, this one, huh? No, this one, 400 microliters. Yeah, the stop time is still 21 and a half. Ah, it is 21 and a half. That must be my mistake from yes, or that must be my mistake from earlier in the week that I named it 15, but I didn't change the times. So it's still running 21 and a half. That's why our time takes longer than the MS method. That's okay. The MS method stops at 15. The gradient will continue, so we'll actually have a good, we'll have good quality data. Just we have to wait for it to finish. That's so where are we in the queue? Yeah, so the data. Actually, let's see. Maybe we can process the data now. We don't have to wait because it will open. Yeah, will open. Yeah, there's the data. Okay. So let's go to analytics and see if we can process. So we can say results new, and we can grab the data file. Be at the end, and no, not that one. This one. Yeah, it's not. You can't do it yet because it's not. It's not finished. So you see, when it finishes, it's available for processing, but now it's not available. So we have to wait last few minutes. Another 3 minutes. All right, almost done. Let's try. Oh, it's still thinking. There we go. All right, new. And just all the way at the bottom. There we go. And we can browse the method with the SMX. There's no degradation products, right? It's just the 100 ppb. Okay, so we'll try that. Open. And we'll say process. Okay. And it disappeared. Here it is. Okay, so don't forget the retention time is going to be different now. So it's going to tell us gray results. So we'll do the targeted screen. So yeah, at that retention time, there's nothing. There we go. That's right. Excellent. Green, green, green. Okay, super. So we changed two things, which as good scientists probably we shouldn't do. We changed the injection solvent to water from methanol, or from 50% methanol to water, so I'm sure that helped. And we changed the gradient away from isocratic to a gradient, and this is actually excellent for your work because the peak is now right in the middle. And basically, when you are doing degradation study, you want your compound to be right in the middle of the gradient. And then if you change your compound, which you will do in degradation, if you make it more polar or less polar, it will still be on the gradient. So that makes a lot of sense. That is actually perfect position, right in the middle of the gradient. And like I said, more polar things will come earlier and they'll still be chromatographed on the gradient. And less polar things will come later and they will still be chromatographed on the gradient. So we just have to change our timing for the MS, or actually we could even leave it, it's fine. So what I would suggest you to do is to run tonight the batch of samples again, and you could do the quantitation again as well if you would like, because I think your peak area will now be slightly better because it's on the gradient. And then tomorrow we can process and we can hunt for those other degradation products, and we can try or you guys can try as an example, the quantitation again. Everybody see that result? That's really now a really excellent result. Everyone understand what we did and why we did it? Yes, okay, great. So I recommend you, okay, so I got 2 yeses from the chat. All right, great. So what I recommend you to do, especially at the beginning, there's a lot of variables on this instrument. And, you'll get the hang of it, don't worry, but at the beginning, use a gradient, and use a gradient that starts at, very low organic, so 5% B we started, and goes up to 95 B. And if you use that gradient and also has a good equilibration at the end, and you try to inject your sample with low organic, I can almost guarantee you 99.999% of the time it's going to look like this. And then once you have a peak like this, then you start to modify gradients to get it how you want. But you always start with something like this so you know that everything is working. That is the most simple system. And I know it's going to be confusing because you're going to read all these papers and people are doing all kinds of crazy things with chromatography. Keep it simple. Start with this gradient first. Maybe, maybe there's a few extra minutes in the gradient or something that we can cut out or whatever. Yes, right? It's not perfect, but we have a nice peak. The data is clear, and you will save time like that. I think they were trying to, I think we have to try to look for the degradation products now. Maybe they were not retained before. Yes, I agree, but I think this sample is only standard. This sample doesn't have the degradation products in it, right?
Yes, right, Alek.
Yeah, there's no degradation products here. We just started with the standard, which is how we should proceed. So let's run those overnight, and then tomorrow, or I mean, you guys are welcome to look tonight, of course, whatever you want to do. But then tomorrow we can go over that together. Does that seem like a good plan now? Yes. Okay, great. So you're going to be chromatographers before you become mass spectrometrists. That's how it works, and that's fine. What we'll do, let's fix our mistake, my mistake, because obviously something is wrong here. So this is 21-minute grad, so I will say file. Oh, I know why. I'm sorry. So I called it a 15-minute, I bet you it's my mistake. I called it a 15-minute gradient because the gradient is 15 minutes, from half a minute to 15 and a half, but the stop time is 21 and a half. And probably I was doing too many things too fast. So then I made the MS method 15 minutes, and it cuts off early. So I think that's the problem. That makes sense to everyone. So the TOF, as I made the IDA method second, right? So we will just choose this one. Perfect, we'll choose that one. Okay. Does everybody see what I did, which is maybe not the smartest move because it's not obvious? I called it 15 minutes because the gradient portion of the method is 15 minutes. But the stop time is 21 minutes because it has that equilibration. So that's where we got confused on the time. Anyway, it doesn't matter because the mass spectrometer stopped at 15 minutes, which was anyway somewhere here near the top, and luckily all of our things came out earlier anyway. But maybe that's a mistake. We should label the runtime 21 and a half minutes. Okay, so maybe we'll make the new batch. So actually you have the samples here, right? Yes, these are the samples. So what we can do, we don't have to do a lot of typing. We can just do a save as, and we can say 20, 20, 12, 16, and then ZABK are these samples, right? Okay, save. And then we'll bring the data files back. Okay, so we don't need to run so many blanks because the system is working now. So we can just do, well, let's do 2. All right, so I will delete those. Okay, and then we'll run all of these again, and we will run with this method, right? And then actually, we don't need these anymore, right? We can delete these samples. Okay, and then that's the right gradient. Now the MS method,
Alek, the injection volume
Yes.
in the LC method is 5 micro.
Uh-huh.
However, Zahra used to put 10 micro, if I'm not wrong.
Okay, we can change that, no problem.
Yeah. Okay.
It is changed here. So actually, I don't know if that's on purpose but you have another column here, which is injection volume, 10, and this will overwrite this. So you have the method. When you load the method, it will be the same, but if you change it here to 10, it will take the 10.
Okay.
So this has priority. So actually it will take 10 because there is 10 written here. I don't know if you guys did that on purpose or not.
Yeah, Zahra specified 10 micro.
Okay, yeah.
Per method, yes.
Okay, so it'll take this then. Okay, so I'm just looking here. So the MS method, we will make this, we'll go back to, okay, we have to change it, right? Because we don't have a 21 minute. Here we have a 21 minute. No, not with the max range. Okay. No problem. I will just fix that quickly. Open. Oh, what happened? Open. Method. All right. So we'll take this one. And everything else is great. We'll just make it 21 and a half. Perfect. Save as. So we have this, and we have here 21.5, and we can say accumulation is 500 milliseconds. Okay, save. And then we need the IDA is this one. So the only change is here, 21 and a half, everything else looks great. Perfect. So it's this one. Okay. And then finally the swath, right? Open. All right. Okay, great. So from here, we'll choose this one. And from here, we take this one. And from here, we take this one. All right. So the only thing left to do is the samples and the position. Sorry, the data file name and the position. Okay, so I can take the sample column. Hope the copy paste is working. And should have that batch. Yeah, batch creation. Okay, so didn't save, huh? Okay, so where do we put sample name? Here. And then this is 20, 20, 12, 16. Okay. And basically, all of that can follow. One more. Then this. And this updates. Okay, and then here we have, so this is TOF MS. So here, this is IDA SMS until here, and here we have swath, right? Looks good. So grab that and just overwrite this. Okay, looks good, guys. Anybody see any errors? Oh, vial position. Oh, the vial positions are the same, right? Because we're going to run the. Oh, no, we have to change the. Because now they are in 50% methanol, right? We could try and see. You mentioned you have samples in water, I think, right?
Alek, I believe her samples are already prepared in water, but the only difference was the elution. She used isocratic elution, and now she's using the gradient elution.
Ah, okay. I misunderstood. I thought these samples in these positions are in 50% methanol, 50% water. No.
Yeah, no. They are
What's
in
wrong?
the ionized water, yeah.
Okay, super. Okay. All right, so the last sample we ran it, the only difference was the elution.
Yes, true.
Ah, okay, I didn't understand that. I'm sorry. Okay, so then we did change only one thing. Okay, good. So we are. No, she remembered that they are in DI water. Okay, okay. All right, super. Okay, good. So I'll save as the batch. So we have it for today, 20, 20, 12, 16. Oh, I already did that, I guess. Okay, this is today's date, so we just say save. Okay, so are we ready to run? I will put the auto calibrate back at every 3 samples. Save. Okay. Looks good to everyone. What's the pressure of the column? So now it's been running for some time. Everything is nice and warm. You need to refill the mobile phase before running. Okay. So what you should do, when the column is fully equilibrated, like this, where it's been sitting and running for 20 minutes, 30 minutes, this is your background pressure. So you should remember this or write it down somehow, 194. And then, if it's more than 5 bars difference, something is not right. So that's a good indication of your column performance and the system performance. So for this method, 400 microliters per minute, starting at 95% A at 40 degrees, 193, 194 is okay. That's your number. So it's a good indication that everything is okay if you have the same pressure every day. Okay, so do you think you can refill the bottles without stopping, or?
Yes, I think it can.
Okay, so just keep track,
Yes.
because you're not really supposed to refill them, but today we are kind of at the end and so on, so to save time we can do that. But at some point close to 1 week for the A and 1 month for the B, you need to actually change the bottle.
Yes.
Okay, because refilling is just like filling up. Okay, so do you want to go ahead and do that? And then we can wait with you if you want and submit, or you can just go ahead and click submit when you've done that.
When I'm done, I will put submit.
Submit. Okay, great. All right, so I think, again, we made a good progress today. We had some troubles, and we solved them, and we talked about them, so this is how it goes. This is part of training. So I think everything is okay. Tomorrow we're going to have even better data, which is how it should be. Unless anyone has any questions, we can finish for today now, and then tomorrow we'll start at 9:30, same time, and we'll take a look at the data that we ran overnight.
Okay.
That makes sense to everybody?
Yes.
Yeah? Great. Anyone have any questions?
No.
No? Okay, thanks. Yes, you're welcome. Okay, so have a nice evening, have a pleasant evening, and I'll talk to you tomorrow at 9:30.
Okay.
Thanks, Alek.
Okay, you're welcome. Okay, guys, see you tomorrow. Bye-bye.